So very good morning all. Welcome to the first lecture of Executive Program in Robotics. So we will just give it a few minutes. I would just let the others join in and then we can maybe start around 10:05. That way we have some time for everybody to join in, right? So very good morning, everybody. All right, so the numbers are rising. I think we'll give it 1 or 2 more minutes and then we'll get started, right? Yeah. Good morning to everybody who are joining in. So yeah, 1 more minute and then we get started. Okay, and I'm hoping everybody can see my screen, can hear me fine. The voice is okay.
Yes, sir, it's audible properly.
Yeah, thank you, Faz. Yeah.
Thank you.
Alrighty, so let's get started. So good morning to everybody who has joined in. Welcome to the first set of lectures for the executive program in robotics. So we are going to have an exciting day with a lot of interesting facts and figures. So before we dive into the lecture, I just wanted to showcase you a schedule which has just been uploaded in the LMS. So hopefully you can see this. This is a PDF of mostly the schedule will be following throughout the entire duration of the course, right? So this has all the details, which weeks you can expect what topics, right? And also the details of our contact email and things like that, right? So this has been uploaded on the LMS, and I've also requested the TimesPro team to share an email with the participants, hopefully through the LMS, which will give you access to all this, right? So you can follow this. If there are any changes to the schedule in the future weeks, like we will get that updated and informed to all of you, right? So this is just a quick note for everybody. Okay, let's get started. So we are at 46. Okay, others will probably join in very soon. All right. So today, what all topics are we going to cover? Like I said, we are going to talk about the introduction to robotics in industry and society. So it's a very broad introduction to the robotics, followed by talking about the historical perspectives. We should all learn about how the robotics field has evolved over time. Has it happened in the past 30 years or 50 years, or how long has been the overall subject of robotics been around, like, and what are the kinds of key events which has happened in the realm of robotics? So we'll be learning about all that, which will give us a perspective of how robotics has developed over time. And also then in the second half, which is after 12:30, Professor Vishwarup would be talking about, the classification of robots, AI, ML in robotics, and lots of interesting trends, right? Like, so that's how the day is going to be looking like, right? So let's get, like into the introduction to robotics. Let's learn about what a robot is, and then we will slowly dive into the history of that, right? So let's get started. Okay, so what is a robot? Robot is, from a definition, it's a machine, especially a programmable by a computer kind of machine, which is capable of carrying out complex series of actions, which is all done automatically, right? So there are some keywords here. It's a machine, which is quite clear. It's programmable using a computer. And another keyword which is there is automatic. It should be able to do something automatically. So if you ask yourself, like, whether a car is a machine, yeah, car is a machine. Is a car a robot? It's not. It's not a robot. It cannot run or function automatically. But is a driverless car a robot? Yes. Yeah, that's something which can function automatically, right? So there are n number of examples which will help you distinguish between a robot and something which would just be an electronic machine and not a robot. So the key term which differentiates that is automatic, right? A robot can be guided by an external control device, or the control may be totally embedded within, right? So you could either have a remote system or some kind of a signaling system through a computer or an app. That could be one of the possible control ways for a robot, or the control may be completed embedded within it. Like that's where you've already coded a system in, and it knows a series of steps and functions which needs to be followed, like a line follower robot, for example. So it has all the details embedded within it, like that if you see a line, your sensor gives you this much information and your robot needs to keep on moving, right? So hopefully this definition of robot is quite clear. It's programmable, it's a machine, it's a computer programmed system, and it's automatic. And its control can be either through an external device or through an embedded device, right? So this is slide 1. Okay, what about robotics? So robotics is traditionally considered to be a branch of engineering and computer science, right? So even though we may think of robots having a lot of mechanical components, electronic components, electrical components, right? But somehow the a realm of robotics has moved more towards a branch of computer science, and there has been a lot of coding associated with robotics. That's why robotics have started getting considered in the field of engineering and computer science. So what does it involve? It involves the conception, design, manufacturing, and operation of robots, right? So that's what the canvas term robotics means. It's everything to do with conception, that where you can figure out what kind of a robot you need to have, what is the design of that robot, how can you manufacture it, and finally, how can you make sure it's totally functional or operational, right? So this is the branch of robotics. Even though this definition is quickly transitioning. So no more, I think, with the the influx of like a lot of mechanical and mechatronics based robotic systems. Are we talking any more about just computer science? It's a lot of interdisciplinary systems which are in place, like you have knowledge from mechanical, you have knowledge from electrical, production, like you name it, and those branches of engineering, even biomedical, right? They're all coming into the field of robotics. So that is what robotics is, right? Like, so this is robotics is a branch of engineering and computer science traditionally, which involves the conception, design, manufacturing, and operation of robots, right? Okay. Next, let's look into the market trends. I like talking about the market before we dive into any topic, because that is what drives the industry, right? At any point of time. Unless and until we know what's going on in the market, we may be, working with a knowledge which is probably not worthwhile for our practice, right? So let's learn about the market, what's going on there. So if you look at the global consumer service robot shipment market segment in 2021, one of the most popular robot has been the house cleaning robot, which I'm sure many of you may have already installed in your houses, right? It's a quite a interesting robot which maps your entire house, irrespective of whether you're looking at staying in a 2 BHK, 3 BHK with different kinds of configurations. This house cleaning robot is able to map it and effectively clean your house, right? So this has become a very popular trend in consumer service robots. Typically, you may not see a lot of penetration within India, because we still have a lot of reliance on maids and household help. But if you look at majority of the Western countries, the maids and household helps are extremely expensive. So the numbers could shoot as high as, like, maybe $100 to $200 a day, like just for a few hours of cleaning. So in those kind of settings where you're spending $800 to $1,000 a month just within with 4 or 5 visits, or that those kind of, like, maybe 7 or 8 visits of the maid, you need some kind of an alternative which you can use on a daily basis, because you want your house clean, right? So it all comes from the necessity. So that's where this robot has become really, really popular in the consumer service segment. The next interesting robot which is very popular in this segment is the personal and educational robot, 31.2%. So these are robots which will basically interact with you. They have lots of educational resources to share, right? So they're getting quite popular in the schools and whatnot, right? Third, which is much lower than the first two, only 0.3%, is the penetration into the hospitality sector. So how does hospitality have to do with robotics, right? So if you look at restaurants in South Korea and a few places in China, you will see that the entire KFC, for example, is run by robots. There may be just one person who is just managing the system, and all the other details, like from, like, making the burgers, heating them up, putting them into the assembly line, is all done by robots, even the serving component. And in South Korea, many of the hospitality, you're talking about the hotels and restaurants where you are looking at robots which are not only into serving, but to escort you, to take you to this place to another, like, there is no receptionist and things like that, right? So this sector is also quite booming in the service robot segment, and we may not see a lot of these like in our own country just yet, but it's just a matter of time when these things will come. So what this also states is, it clearly states that there is an opportunity to invest in that kind of an area, which is a little untapped compared to the other areas, which are with 68.4% and 31.2%, right? After that comes logistics. So we are all well aware of how logistics is a very interesting industry, so uh, yeah, there is a quick question, so I can just quickly take that, and then I'll try to, look at this. So maybe this question is this. So none of the questions are stupid. I think it's lovely to have questions from all of you, but can an automated process categories as a robotic process. Yeah, so it depends, what is that automated process exactly doing? Like, is it so automated process can have very different realms. Like you could talk about a process which is just totally automatic. It's doing the same task again and again. Yeah, that can be robotic. That can be well considered robotic. But there are certain things which are automatic and may not lead to, functions or attributes which are robotic. So in those cases, it may not be so. So as we get into more and more examples, I think this component will be much more clear. And also, Professor Vishwarup will be talking about the classification robots at length. So I would just request you to hold off your question for a little bit and we can just revisit that, right? Yeah, you're welcome. Yeah. All right. So next is, after the hospitality sector comes the logistics. Logistics is a huge sector. Think about Amazon, for example, right? So in Amazon, you have n number of parcels, packages, which needs to be taken from one location to another. So where is robotics coming in, right? So these are people who are taking shipments from one place to another. No, not really. So there are certain positions and places where robotic arms are basically helping out in the packaging, moving one package from another location, this location to stacking in another location. So there's lots of these operations like within this shipment industry and logistics industry is taken care by robotics, right? You may not see a lot of penetration, like which is just very clear to your eyes, like in front of you. But if you look at these particular industries, you'll be seeing more of the logistics taken care by the robotics, right? But still the market is quite low. If you are looking at the overall market, you're just looking at a 0.07% penetration into the market, right? So, which is quite on the lower side. That clearly states that this serves as a huge opportunity for starting up or investing in this sector. Next sector, which is very close to my heart, is the medical sector. But if you look at how much of robotics penetration into the consumer system has come into the medical, it's only 0.01%. So there is so much scope of robotics into this segment, from collaborative robotics to robots which can help you with, mental health coping, to robots which can help you with carrying of one parcel or carrying of few surgical instruments from one part to another, right? To lots of surgical robots, which are Da Vinci kind of robots, which we will be talking about at length. See, all these robots back together in a hospital setting or a clinical setting is just accounting for 0.01% only. And all other applications, think about so many applications which are there, defense, agriculture, you name it. These are only part of less than 0.01%. So this is where the robotics consumer market seems like, right? So there are some popular trends which are selling like a hot cake, and rest of the things are just catching up, right? Yeah. Yeah. So I will just take another quick question. So whenever I see the meeting chat, it's easy to get distracted, but I'll just take this question and I'll request everybody else to, put on your questions. That's totally fine. I'll just take them a little later cycle. Otherwise, I just keep on going back and forth. So I'll just quickly take this question from Mathangi. I think, why is the penetration low in medical? Isn't it one of the areas where it will be most effective when put to use? Yeah, you are right in the second point. It is one of the areas where it is extremely booming. Think about any surgery which can be conducted with a robot, which is super accurate compared to the different realm of doctors where you can have. And also lots of collaborative setting-based robots, which can be really popular in this segment. But the penetration is low because this has not been put to use just yet, right? So if you look at the Indian market, for example, you will see robotic surgeries are there, but not super popular, right? If you look at the hospital setting, do you see any robot around? Probably not. So it has not penetrated the market just yet. But if you look at the West, this has already started happening. Many of the hospitals are having robots because they have lack of manpower. Manpower is extremely expensive if you look at the West, so they would rather have a robot, talk to you in a daily basis, like, where you're trying to cope up with a disease. Maybe it's a terminal disease and you're trying to cope up. Surgical robots are coming more and more into the market because doctors are expensive. Yeah, even defense sector sees very, very low penetration, even with drones and so many technologies. There is so much to be done in terms of exoskeletons, humanoids. I'll be talking about all these, right? So they have resources and also the engineering capability, right? They do. That's a very important point, but it is actually a very surprising attribute. So if you look at just from yesterday, there was a visit from the army. They were trying to get some exoskeletons and other defense equipments built up. They visited IIT Delhi. uh, they were saying that there are no exoskeletons in the market, right? I will talk about what these things are, exoskeleton and all these terms. They were saying there are a lot of drone systems in the market, but that defense level capabilities, even though you're seeing drones all the way around, their possibility of detection, 3D mapping, these kind of things are still evolving. Accurate tracking of like the enemy locations. So there are so many things which are still evolving. So there is some penetration, but compared to the other larger chunks, they're quite low. So the defense sector is like pouring in more money into the segments, like to improvise robotics, at least from the Indian setting. But if you are looking at China, where data is limited, they are just booming. They're creating humanoids. There is so much into the defense which is going on. So yeah, keep putting your questions. I'm not going to look at it, this meeting chat for a while, and I'll come back to all of your questions later on, right? Yeah, thank you. All right. So this is the global consumer service robot shipment market. So what does the shipment market means? It means what robots were shipped during 2021, let's say. That clearly states that these robots are more popular into the consumer segment rather than the others, right? So these are some initial market trends. Let's look further into the specific market trends. Let's look at the medical robots market. We were just talking about it for a moment back. So the CAGR, which is known as the compounded annual growth rate, which clearly defines how a market is growing over time and what are the key projections of a market growth over time. So the global, if you're looking at the overall medical robotics market, 2023 to 2024, you're seeing quite a surge. And the projected market by 2029 is 16.1% increase. And these are the distributions like in the different segments. If you're looking at North of America, Europe, Asia, Pacific, Latin America, Middle East and Africa, these are quite small segments. The largest segment, if you look at, is North America, followed by Europe, right? So these are very common trends, like typically. Next is the pharmaceutical robotic market. So how does robot get into the pharma? So they are very much involved in sorting of, the drugs, like typically. So let's say there are so many tablets or pills which are coming out in full flow, like they're getting built and like they're quickly coming up, sorting of these pills, putting them into the right package, and also picking up a few pills and testing them. What's the potency of that? Like, what is the effectiveness of all that? So pharmaceutical robotic market is just booming. It's currently at a CAGR which is projected till 2033 of a 6.7%, which is not super high, but still it's a market in which a lot of us can innovate robotics. And as we get more into this course, we will know where exactly the opportunity lies, what exactly can be built, which can be beneficial for the big pharma, right? But if you're looking at the overall market, you're looking at 2023 of $225.2 million market, and which is expected to rise to $431 million market by 2033. Not a super high rise, it's almost double, right? But still is a market to be looking at, right? So the types of robots which are going to be there and which are already coming in are traditional robots and collaborative robots. I'll explain what these terms are as we go through the lecture today. Traditional robots are common robots which just work in a workspace typically by themselves. Collaborative robots are working in a shop floor or a factory or in an area where they have to interact with the humans, right? Those are known as typically collaborative robots. So from a pharmaceutical robot market standpoint, you're looking at applications like picking and packaging, drug inspection, like I said, lab testing, and things like that. If you look at the regional analysis, the North of America, which is the US, is the largest in adopting robotics. I'm not saying they're largest in building the robotics, they're largest in adopting the robotics. So I think those terms should be clear. Next is Latin America, Europe, Asia, Pacific, and Middle East and Africa. These are the key areas. But if you look at the penetration of robots into any market, the least is in typically the Middle East and Africa, and like typically in the Indian and like similar setting close by, like Malaysia, Thailand. These are the lowest penetration of robotics so far, right? So that clearly presents a huge opportunity, and many of us may not be aware of that. Okay, the robotics market is not looking so booming or so interesting as we think, like the data stats show us. Let me tell you this is a totally wrong information. If you interact with the industries right now, every industry, you talk about it, like, be it automotive, agriculture, defense, medical, everybody wants robotic engineers. Everybody wants hardcore engineers who can build robots, who can help them with the solutions. And this is not from some newspaper article. This is from personal speaking with a lot of companies. So they are building so many parts, and components of the automotive systems, like subsystems, agricultural systems. They're wanting to replace the manpower. That is the key goal. They want to cut out on this 10x manpower, like, and just get done with it, like with a robot. The benefit of that is manpower can make errors, right? Somebody who is working for more than 7 or 8 hours is prone to be tired and making errors. But the robots are not going to be making errors, right? And they can work 24/7. So your production just goes 3x or more. That's what the companies are looking at. So I have recently visited a company where they gave me a clear math that I want to replace this 20 people with a robot. Can you build this within this particular number, right? Like, so these are the total salaries of these people. Let's say they are making total of, let's say, 1.5 CR or something, and I want to replace this with a robot. I'm going to give you this much amount of funds to build this robot. This is how the market trends are actually changing, which we may not be aware of right in front of us, like, because we do not see a lot of robots in front of us, but the industries are quickly shifting. We'll talk more and more about it. But some of the areas of interest into the medical robotics or the pharmaceutical robotics market is into the report segmentation by components, like instruments, service systems. Like, these are quite well defined by the robotics. If you look at the market statistics, you're looking at 17.37 millions with a high CAGR of 14.2. This is from the broader market. Okay, next is the interesting part, global AI in robotics market. How is AI getting into the robotics market? We are all well aware that AI is the most popular trend. So majority of the AI-based systems are into the service robots, less into the industrial robots, right? So what is a service robot? What is an industrial robot? Industrial robot, typically you can think about that large robotic arm which is building, vehicle components in a factory. So that is the easiest way to visualize what an industrial robot is. Service robot is your robotic vacuum cleaner or your robotic system which talks to you, an educational robot, right? So majority of the global AI systems are getting integrated into the service robots rather than the industrial robots, because there is a reluctance of industries into adopting AI unless it's very much proven, because they are fine with whatever they're doing with robotics. They are much more resistant to change or adopting AI than compared to service robot segments, which are quickly evolving. Yeah, I'm just going to not look at it. So just hold off on your questions. I'll take that up later on, right? This market is huge. We are looking at 28.12% CAGR, which is a massive CAGR. The forecasted market by 2033 of global AI in robotics is $146.8 billion, which is not a small value, right? 2023, we have already passed. 2025, I'm sure the number is a little higher because these statistics I pulled up around 2024. So if we assume that it's $20.2 billion right now, we are looking at a $146.8 billion by 2033, which is not too far, right? And service robots are going to be the most popular with AI-based tools. So what this tells you, this graph, the takeaway of that is, if you're going to align your robotics knowledge or your knowledge in AI, you would rather look for consumer companies, like, service-based companies which are trying to build robots for the market, for the general people, rather than trying to jump into the industries and getting an insight that can I integrate AI into the system. The trend clearly tells you that industrial robots have a lower, penetration of the AI as compared to service robots. So this is where the jobs would be more into the service robot segment, right? Okay, let's look further. Okay, let's look at the global agricultural robotics market forecast 2022 to 35. So key areas of interest, right? You're looking at Asia Pacific, Europe, and North America, right? If you're looking at these markets, all these are very popular market for agriculture, right? India is already seeing a lot of robotics into the agriculture. So what are you looking from the market by application? If you're looking at 2021, the plans are typically quite small, and in 2030 you're looking at larger production typically. So you're focused on harvest management, dairy and livestock management, crop production, and other applications. I'll give you a very small example. So I spent around 8 years in the US, right? Like, and during that time frame, what I've seen is typically these Walmart kind of settings, or most of these larger, supermarkets, which are selling vegetables and everything else, right? Those have all varieties of these fruits and vegetables which are there. You would not see so many varieties in India. Typically, they're the similar end. So typically in certain areas you will see organic systems, and in the other areas you will see onions, you would see tomatoes, like all sorts of vegetables which are much larger than size. You would never find those sizes like in India. Typically these are much larger in size. But what I've seen is, like, recent times, if you look at 1 or 2 years, there are 2 or 3 types of vegetables which are coming into the market. If you go shopping, you will probably know what I'm talking about. So you will see different colors of the carrots with seasons, right? Like, you will see different sizes of the apples, oranges, and things like that. So why is this happening? This is happening through a lot of robotic production setting, right? There is a lot of upscaling into the production where artificially things are getting created. So that is the major goal. Can we involve robots into this market where they can do the harvest management, dairy and livestock management, crop production, increase the production, so that, because the consumption is going up day by day. So if you're looking at 2021 to 2030, you are looking at UAVs and drones, which are to be used for a lot of applications, from spilling the fertilizers to making sure it can track what is the agricultural condition, like, what is the crop production condition in certain areas in large fields. You're looking at milking robots. Why would you do that? Like, there are so many people who can be employed into the milking industry. Why would you want a milking robot? Because this makes sure that the performance of milking is much higher. And second component is, there is no human error component. And third is, you can get rid of so many people. That's what the market is looking at. Can you have robotics into the system so that you can get rid of 10 or 15 people, right? Automated harvesting systems, right? Eventually, these are going to replace a lot of farming based systems, right? Like, these are completely going to be automatic. They are going to have multiple steps and procedures included into it. Driverless tractors. Why would you have that, right? So tractors are just doing fine, right? Like, the villagers or the folks, like, who are into the fields know how to drive a tractor. Why would you have a driverless tractor? That's because of the long-term vibrational effects. So somebody who is driving a tractor typically experiences spinal cord issues, like, back pain, injuries to the different components of the body. So it's an occupational hazard. So places where you have humans which cannot perform, tremendously well over a long period of time, those are the places in which, if you look at any sector, be it agriculture, be it defense, be it medical, those are the locations in which robotics is coming more and more. This is just a perspective building which we would have like based on the different examples, right? So driverless tractors are going to be very, very popular in the upcoming years or so. They're already getting built. Which are the key companies I'll have to look into, but there are many companies which are already started investing into them. Other types of robots are informational robots. Can we have certain informational robots which tells to a villager in a local language that these are the different cycles within a crop cycle and what kind of fertilizers, what kind of utilization, what kind of water content, all these things, how they have to be optimized, right? This can come from a central repository. Right? All these different attributes of robotics is coming into the agricultural sector, right? Some of the top companies here which are already invested into robotics is ACCO Corporation, Autonomous Solutions Inc., CNH Industrial, and Deere and Company. Deere and Company is a very popular company which makes all kinds of like, typical automotives and tractors and different kinds of like, harvesting equipment, right? So these are some trends into the agricultural robot market. Let's look at the global hospitality robot market. What are they doing? So market growth is going to very highly accelerate. 11.6% CAGR is quite high. The incremental growth from just 2021 to 26, 26 we are going to reach within a year. You're looking at 291.74 millions. The market is quite fragmented, right? Because many are not adopting the idea of, using robots into the hospitality industry. As a country, if we look at it, we have just seen a lot of penetration of people who were typically focused towards like all the professional jobs are getting into these kind of markets, right? So a lot of the people who would not typically choose a option of like the hospitality sector are going into that sector. So the market is quite fragmented. Will India typically adopt robotics into the hospitality sector? My opinion about that is like a little divided. Like I'm not sure like probably if that will happen in the next 5 or 10 years, but it may happen after that once the manpower cost keeps on going up. So one thing which we commonly see into the market is look at the salaries. Like typically just compare that last 10 years salaries, like they have skyrocketed, but you could always say the inflation has gone up and a lot of other things have changed. So as the salaries keep on going up, all the salaries are going up. Like if you are trying to hire a maid, if you're trying to hire an operator, if you're trying to hire anybody, the typical salaries where you could pay somebody 5,000 has now probably gone up to 15,000, 20,000, 25,000, and so forth, right? So as the salaries and the prices go up, robotics are going to quickly take up this market. This is what happened in the West. And I say this very often, whatever happens in the West, very typically within 10 years time frame gets adopted in the East, right? And right now the divide is slowly reducing. That's what I've seen like from the global trends and also from a personal attribute. Like, certain things which happened in the US and right now happening in India, but like, that divide is quickly reducing. Like right now, something happening on that side may happen within a year or two. And of course, like the administration and socioeconomic issues are always there, right, to drive it. So the growth contributed by North America is 37%, and the growth for 2022 was 11%, right? So this is into the global hospitality robot market. Okay, now comes a very interesting market, which is the highest CAGR ever reported, even higher than AI. This is known as the humanoid robot market. I will be having some lectures on humanoids, and you will be very surprised to see that these robots, which are known as humanoids, are not only human looking, they are exactly behaving like the humans do. Their gait pattern, their walking pattern, their behavioral systems, like how they move their arms, move their eyes, they're exactly like the humans. That's the level of robotics which is the market scene, right? So the humanoid market is increasing at a massive level of CAGR of 50.2%. Unimaginable CAGR. CAGR is a very important metric, like I said, to determine how a market is growing. The global humanoid robot market is expected to be worth USD 13.8 billion by 2028, which is just 3 years from now, less than 3 years, right? Growing at a CAGR of 50.2%. If you look at 2022, 23, of course, like it's just post-COVID, things are changing. There has been a lot of wars which are happening all around the globe. 2028, this is what the expectation is. North America, Europe, Asia Pacific. Asia Pacific is going to be typically driven by, majorly the other economies like, which are Chinese focused, or like, some places like Malaysia. India may also catch up like with these kind of trends. But it's good to know if you're planning on creating a startup, deep tech startup in these areas, like these are some areas to focus on. So why humanoid? Why would you need something like a humanoid when the humans are all there to do all the job? Two, three things, very important key points. Think about an army which is trying to fight across the border, and the army is going to fight in a very extreme condition. Typically, we are surrounded by, mountains. It's a very extreme condition to fight in. So after a while, like let's say 7 or 8 hours, you need certain amount of rest. Think about a humanoid. This can fight much more strongly. There might be so many force sensors. These are intimidating to look at, and they can fight for 24 hours. They can get into terrains which can be extremely fatiguing, like for most of us. So if anybody has watched the movie like Universal Soldier or Terminator, you would almost see the glimpses of that within these humanoids. So the defense sector is extremely engaged into building humanoids, because these are the next step of things. If you want to fight with some countries like 24/7 with the highest amount of, manpower, this is the humanoid power which they're trying to build. And very much in the stealth mode, many of the countries have already started building it. If you look at China, there are factories which are completely run by humanoids. These are known as ghost factories. This may not be very much believable, but there is a recent news which leaked some of that information, right? Because China is a very closed environment, like the news doesn't come out. Even during the COVID, nobody knows what is happening inside, right? But they have already built a army of humanoids which are ready to be deployed into the industry. They're working 24/7. So think about such a system coming into places like India. It could completely change or transform the market, how the manufacturing sector works. Think about an assembly line for an automotive industry, or assembly line for something, a pharma industry, completely replaced. So what kind of jobs are going to get replaced? The ones which are routine tasks, which are fatiguing. Like after 8 or 10 hours, they're just keeping on doing the same things. What kind of new jobs which are going to get created? Software, people who can build the actual structures of the robots, like who are into the product development, mechanical structures, mechanical engineers, electrical engineers, electronics engineers, and of course the ones who are using AI and machine learning. That's also going to be a very popular trend. And robotic operator, robotic repair specialist. So these are some of the jobs which are going to get very popular as we see this huge shift in the market. Let's look further. Okay, now that we have learned a little bit into the market, some of the very exciting trends, and many of these may have been an eye-opener. Let's talk about what do we mean by robotics in industry? Just given you an example, and what do we mean by consumer robotics or collaborative robotics? Let's talk about it. So industrial robots are the most popular robots which have been there for the longest times. They are heavy-duty machines, typically designed to automate the manufacturing process. So the plant which you're looking at is not Tesla, but there could be a market which is, if you look at the Tesla manufacturing, it's very similar. All the robotic arms are doing all the different steps. Look at the same in places like Tata Motors, which is one of our largest producers of the automotive segment, right? I personally worked in Tata Motors, like so 2010, like which is 2010. You know what I saw during this kind of an assembly line? In place of the robot, a single robotic arm, there were 7 to 10 workers who were in every station of this particular assembly line. And out of the 7 to 10 workers, how many were working? Just one or two. Rest were just chilling, trying to just put a screw in or put something in. If you look at 2025 right now, majority of them have been replaced. All the stations have been reduced by like maybe one or two operators, one as a backup and things like that. Many of the robotic systems have come in, into majority of the automotive market, not completely replaced it, but it's already work in progress. So this is how the robots are going to replace all the routine tasks. So industrial robots were typically built with that notion. So can it replace the human efforts where human can really get fatigued? Extreme conditions, things like welding. Nobody wants to do welding, right? Because it's hazardous to the body, right? Like it can be problematic. You can burn yourself. Nobody wants to do an operation, heavy machinery operation, which can lead to an occupational hazard, occupational injury. So those are those extreme conditions where robots can take over and they can perform the job much better for 24/7. They are equipped with at least one robotic arm, most of these industrial robots, and often complete repetitive or dangerous tasks. These are the two keywords, repetitive and dangerous tasks in warehouses and factories. These are the robotics, industrial robots, how they came along. And you can just replace the scenario with a pharma industry. You can just replace the scenario with a surgical device industry or a medical device industry or another industry which is building a lot of these robots, like, consumer industry. But the robotic arms stay the same, just their operations or steps change, right? So these are the industrial robots. So let's look at some interesting trends, and I think this would be valuable for all of you. Let's look at the countries with the highest density of robotic workers. Robotic workers. So installed industrial robots per 10,000 employees is a unique number. So every 10,000 employee in that country, there has been an installed, one industrial robot has been installed into the manufacturing industries in 2019. This is the trend. Let's look at some of the top countries. South Korea, right? So 855 industrial robots per 10,000 employees, right? This, which is quite a high number. So you're looking at almost like 1 in 10%, like is replaced by robot. If you're looking at Japan, that's the next. Germany, Sweden, US, Italy, Belgium, Spain, China, France, Canada, Switzerland. There are many other countries. India, Middle East, none of them are here, right? So India has been historically a country where we like to wait and watch and see typically how the world is behaving in terms of adoption of a new technology. And then once it is a worthwhile solution, we jump into it. That's typically been the global stance, right? So that's where I think some of these robotic startups or robots are getting built, but they are closely watching these trends in the industry. So if you're looking at this, like this is 2019. So by 2025, I'm sure this trend has really gone up. And many of the industrial Indian companies have started investing into all that. They will not talk about it because many of these robots may be just coming all of a sudden in 2026, 2027, and so forth, right? But they will not be talking about it to avoid competition. Because if everybody starts putting things in the press that I'm building the humanoids, I'm building this and that, there will be a lot of market competition. So that's typically to avoid that competition. So if you look at the top activities in which these industrial robots are working in, this is another very interesting trend. The top activity across all the areas is material handling. So material handling is a very big challenge where robotics is coming into the picture. So the projection from 2022 to 2032 is almost more than linear, it's non-linearly increasing, right? And you're seeing the major block of material handling still almost increasing proportionally, right? So what is material handling? Material handling is when you want to handle certain jobs, handle certain materials, putting one part of the material to another. Like let's say one material has to go through different stages of operation, like certain chemical dips, maybe, certain kinds of operations like brazing, sintering, like, they have to be molded in a certain way. There are so many steps, like, casting, like all these attributes are, all these material handling possibilities in across the industry is taken care by the industrial robots. So the operators who are currently into the material handling industry are going to see a lack of their or loss of their job in the coming years. Right? Next is welding and soldering. These jobs are getting very quickly replaced by robotics, industrial robotics. So somebody who is a welding expert or a soldering expert is most likely going to lose their job in the next 10, 15 years, right? Assembly, disassembly. Industries like, big packaging industries or industries which are dealing with packages, so many packages, be it Amazon, be it shipments, like large scale shipments from the, all the shipyards and things like that, where globally the world is connected. So all these assembling and disassembling components which are done by humans, like they're going to be quickly replaced by with robotics. Palletizing, packaging, painting, dispensing, milling. What is milling? Milling is cutting through a material. This is a mechanical operation. So what do we see commonly here? All the operations which are routine tasks, which has to be done with precision and which can be done with a robot very comfortably, doesn't need a lot of human brain. Those kind of jobs are getting replaced by industrial robots, and these are the target areas of the industrial robots. And this is in sync with what I found from the industry. Every company is trying to automate those components. That can I replace this 10 people who are handling the different steps of the material with one or two robots, right? So hopefully this part is clear. These are the top areas of interest across any kind of disciplines in robotics. And these are the top countries of interest, which also tells you that if you're interested in pursuing maybe, further studies in robotics or research in robotics or get into the companies in robotics, these are some top countries to look into. And of course, there is an untapped India where the robotics system is just starting. And I think there is a lot of skilling and reskilling which is taking place right now, which is going to set us up like for the upcoming market in robotics, which is just evolving very quickly as we speak. Okay, so with that market knowledge, let's learn about the 5 different types of industrial robots. How do we classify industrial robots, right? So there are more than 5 types of industrial robots, but the most common ones should be classified by their mechanical structure according to the International Federation of Robotics. So there are certain federations and groups which basically, monitor the area of robotics. So the first type of robots are known as Cartesian robots. These work on 3 linear axes using the Cartesian coordinate system X, Y, and Z, meaning they use the 3 sliding joints to move up and down, in and out, side by side. Cartesian robot is most commonly used industrial robot. What are some of the examples? 3D printers. So 3D printers are actually Cartesian robots. CNC machines, Cartesian robots. Because this goes from one location to another along the X, Y, and Z and performs certain tasks. One picture on the top here shows one of the examples of the Cartesian robots. Right? They may have n number of operations. Their operation could be printing, cutting, doing certain other kind of drilling and so forth. But like the basic fundamental, how their operational fundamental is Cartesian. So that's known as a Cartesian robot. Next type of robot which are there in the market are known as SCARA robots, which is broadly known as Selective Compliance Articulated Robotic Arm. These robots have typically 2 parallel joints that provide compliance in a plane. So that's the second robot which you're looking at on the right side. From the top, you're looking at the second one down, right? The SCARA robot is commonly used for assembly application and specializes in lateral movements. These kind of movements, right? Sideways movements. So they are not able to have linearly go from one place to another. So how would you use such robots? What is the use of SCARA robots? They're from picking and placing. That is the main operation. Picking a job or picking a package or picking a part, picking a screw, let's say, from this location, putting it in another place, right? So these are the main jobs of SCARA robots. So if they are not so versatile, why would we use them? Because in certain places, that's the only job which the robot is supposed to do. We do not need a complex robotic arm to do this job of picking and placing or installing something, right? So that's where the SCARA robots became very popular in the industry. Next is known as an articulated robot. So articulated robot is the most popular industrial robot which you may have seen in many places. With anywhere from 2 to 10 or more joints, articulated robots are connected to the base with a twisting joint. So the base can twist in any direction, right? Resembling and the rest of the part is like a human arm. They are commonly used in packaging, painting, metal casting, all sorts of industrial applications. So these are common examples. Robotic arms like are all around the place, like be it in automotive, agricultural, you look at defense applications, you look at medical applications. Everywhere the robotic arm is like the most common industrial robot you'll observe. Okay, next robot is known as a Delta robot. Delta robot is the fourth picture from the top, which you're seeing a little towards the right. This is heavily used for manufacturing in the food, pharmaceutical, and electronics industries. These looks like spiders, which are connected with a common base. The Delta robot is typically used for fast picking and placing applications due to its high-speed precision. So what does a Delta robot look like? Have you probably maybe visited a mall and you may have looked at some of those games where you put some cash and it has this picking option and it picks up a soft toy, like it looks very much similar to that. Much faster than that, much more accurate. So the goal is these are spider looking robots which can very quickly pick up certain things, right? Pick up certain pills, like, these are small packages, components, electronic components. They can be very quickly picked up and placed in another bin, placed in another place for probably for the testing, random testing, some other operations, control test. Like there are so many options, but these are widely used in the food packaging, pharmaceutical and electronics industries. Right. The last one is the cylindrical robots. This is considered a good fit for tight spaces. So these robots are not going to roam around or have a lot of space usage. This compact robot features at least one rotary joint and for rotational movement and prismatic joint for linear motion. So typically you would see them in testing equipments like universal testing machine, certain material testing systems, which are automatic. So cylindrical robots are typically parts of testing systems or just picking something up along a certain direction. Common cylindrical application, like I said, like are also used for assemblies, die casting, machine loading, unloading, which is the testing, right? So these are the 5 types of robots which we are talking about: Cartesian robots, SCARA robots, articulated robots, Delta robots, and cylindrical robots. You don't need to remember all this. I'll be sharing all the slides, but it's good to know what are the key categories of the robots. Let's look further. So the next component is robotics in the society, which is quite different from the industrial robots. Robots are used in society in various ways, ranging from healthcare and transportation to entertainment, right? So some interesting and key robots are bomb disposal robots. Think about, still we have that thing that where in the defense sector, if there is a bomb somewhere, somebody needs to wear that complete suit, and there's a bomb disposal squad which goes on and like tries to defuse that bomb, right? Which poses a lot of risk. What if the bomb goes off? Somebody may die, right? Like, so typically to avoid such difficult positions or difficult conditions, like, can there be a robot which gives a live feed and can just go in those locations? Even if the bomb gets diffused, it is fine because the robot died, right? And it could effectively give you all the instructions similar to a bomb disposal squad, and probably can go and perform certain operations of cutting a wire or whatever needed to be done to dispose that bomb, right? So bomb disposal is used in the military setting where robotics is getting more popular. One example. The other industries are healthcare industry, transportation and logistics, construction infrastructure, entertainment and hospitality, right? So there are a lot of robots which are into the entertainment and hospitality and also in the medical arena. I'll give you an example. We are in the era where most of us are living in a nuclear family kind of setting, right? So most of our parents are growing old, like they may be living with us, but in most cases they are not. Like we're in different cities. This kind of trends have already been observed by majority of the cities in places like the US, right? In US, it is very often you will observe that there is a large house and there is one person who is just very old person who is just living there. He may have lost his wife, due to age, and none of his kids are around. So this person to be mentally okay, they may be suffering from a disease because they're at their 80s or something. There are a lot of robots which are getting deployed, which can talk to them and just ask them, hey, how is your day? How are you doing now? Have you taken your medicines, right? So what kind of steps are you taking? Are you exercising? So these robots are getting very, very popular. We may not see them right now in our society, but like I said, it's just a matter of time. If you want to see what the market trends are, what are the industrial revolutions which are going to happen, look west. You will see the trends which is going to come in. So this is where these robots are getting very, very popular. They're sometimes placed in the entertainment industry, sometimes into the hospitality industry, and sometimes into the medical industry, mental health industry. Also, robots in very, very crucial areas like mining industry, robots in the military are getting more and more popularity. Why mining? Because mining is a very risky job. So just a common example, if you are looking 15, 20 years back, and you're searching for a job which is the highest paid around the world, you'll probably find a job in a very remote place in Australia or a remote place somewhere in Africa where you have to go few kilometers like down the ground and probably do some mining, right? Or in certain locations. These are extremely risky job. Like there is one landfall and you're gone, right? Or there could be in certain cases like, there is an oil rig and there could be fire, right? So these kind of industries which are posing a lot of risk to the human life, that is where robots are getting more and more popular. And these jobs are going to eventually get replaced with the robots, right? Military, of course, there is a military tactics and there are a lot of things. Basic military setting is not going to get replaced, but like I said, there are different layers of things which are already happening, like drone technology. There are so many other technologies which are for tracking, detecting the enemy. And then there are the humanoids which are getting built for fighting these wars, right? So robots are, as we speak, they're coming into the society more and more. You're seeing another picture here where this kid is trying to talk to a robot. She may be very lonely and she's like just trying to speak to a robot. Maybe both her parents are working, right? This is a common problem, like, right, where the society needs people to talk to. And the other example here at the bottom is this nurse is basically trying to help out 20 or 30 patients, you know, due to limited manpower. If you look at the West, again, this is a scenario. In Indian setting, you look in a hospital, it's extremely loaded, overloaded, right? But you look in a hospital in the West, even for getting an appointment, it takes a while. Manpower is extremely expensive. So that's where they're trying to get more and more robots into the system. That this nurse may be taking care of 20 people, and it's not possible to observe and look into all of them. So if this robot can help out with some disposals, bringing in of medicines like injections and things like that, reminding of certain things. These are known as collaborative robots. So robots are coming into the society before we actually know about it, and these are happening quite now, like in the West, but they are coming in slowly and more rapidly into the Indian continent as well, like very, very quickly. In the next upcoming years, like we are going to see more of these, right? Okay, so that hopefully gave you a initial introduction into the robotics, what the market looks like, what are the key trends, what is an industrial robot, what is a societal robot, and also the different classifications of robots. Now we are going to switch gears and let's talk about the history of robots, right? How have they evolved over time? Let's talk about what are the perspectives, what are the some of the things which have shaped the area of robotics, and this will give us a lot of insights into the innovations which have happened over the years. So let's get started. Okay, so history of robotics dates back to 250 before Christ. So robotics is something which did not happen like 20 years back or 50 years back, like it's way before that. Stebius, like an ancient Greek engineer and a mathematician, invented a water clock, which was the most accurate for nearly 2000 years. So that's one of the earliest glimpses of robotics where everything was automatic. So you could always say that this did not have any electronic components. So how is it robots? But it was automatic. They created a system which was probably mechanical, but fully automatic. Electronics have come into the market quite later. We'll get into those timelines, but this is one of the earliest glimpses of adoption and possibilities of robotics, right? Then we are looking at 60 AD, which is 60 after death. Like, so Hero of Alexandria designs the first automated programmable machine. This was known as automata, which was made from a container of gradually releasing sand connected to a spindle by a spring. So the keyword here is automatic. There are so many mechanical devices, but are they automatic? They're not, right? So the key goal here was, can we use some mechanical assemblies and make an automatic system, right? So by using different configurations of these pulleys, it was possible to repeatably move a statue on a predefined path. So the goal here was quite clear. First goal in 250 BC was to build a clock, right? So that people can keep track of the time. Second idea was, the Hero of Alexandria wanted to make something so that they can move a statue. The human efforts were not good enough. The human strength was not good enough to move that statue. So they wanted to do it automatically for the very first time. So the idea was to use the gravity, the principle of gravitation, where sand is loaded from one place to another, and that creates a pulley movement, and finally that entire rope is able to pull that particular device or particular statue from one location to another repeatedly. So the human efforts are completely taken care of. So 60 AD, this was created using a completely mechanical system, an automatic system. 1738, quite fast forward, we are looking at Jacques de Van Vucanson. Like, so many of these terms are quite difficult to pronounce because many of these are you're coming from the European or Latin influence. So builds a mechanical duck, which was made of more than 4,000 parts. This was a completely mechanical system which was built out of 4,000 different parts. Such a detailed system. This duck could quack, bathe, drink water, eat grain, digest it, void it. So look at this interesting system. So this duck had a bunch of mechanical systems which allowed it to automatically function just like a normal duck, just like an actual living duck. So this was one of the very interesting automatic systems. Whereabouts of this duck are unknown today. What does it mean? The duck was probably, lost. Somebody might have stolen it. Right? So this is one of the earliest history of robotics. Next is 1805. A doll made by Malardeth that wrote in either French or English could draw landscapes. This very creepy looking doll, like not very, you would probably see this in some of the movies. This was made by Malardeth that wrote either English or French. Think about a doll which can write. It's very, very interesting. Using just automatic robotics, like just mechanical systems, they could build it. 1805. Next, looking at 1898. The first radio-controlled submersible boat was invented by Nikola Tesla, right? And this was a completely mechanical with some radio-controlled systems, which was totally automatic. 1921, now comes the interesting era. The term robot was first used in 1920 in a play known as R.U.R, which is known as Rosam's Universal Robots by Czech writer Karel Čapek. So the robot term was actually not built out of innovation. It was built in a play, right? The plot was simple. Man makes robot, then robot kills man. What does it tell you? It's a very simple plot, but it tells you that robot is considered as an evil device at that point. That was the perspective about a robot back in the day, 1921. We're not looking very much behind, but almost like we are looking at 100 years-ish, Many movies that followed continued to show robots as harmful, menacing machines. So robot comes from the Czech word robota, which means servitude or forced labor. So this was the invention or the birth of robotics. The robot was considered as something which is more of a forced labor or servitude. So very interestingly, what you will observe during the history of robotics is many of the robotic trends, like development of sensors, development of how the robots should look like, what kind of joints it should have. Many of these things were influenced from movies and plays, and not only through engineering or physics-based innovations, right? So I'll be talking about some of the examples where, Terminator movie has given a certain insight to robotics. Star Wars has given a certain type of insight to robotics. So this is how the robotic realm has evolved. So many of these things are not derived from technological advancements, right? Okay, let's look further. 1940s, Sparko, the Westinghouse dog, used both mechanical and electronic components. So this was the time where electronic and mechanical components were coming into the system, 1940s. 1941, Isaac Asimov, introduced the word robotics in the science fiction story, The Liar, right? So again, a science fiction story, like this word robotics was first introduced. So if you're interested in robotics, you may have heard about Isaac Asimov, right? Like one of the nicest, book back in the day. 1948, William Gray Walter builds Elmer and Elsie, two of the earliest autonomous robots with the appearance of turtles. The robots use simple rules to produce complex behavior, right? This typically looks like our mechanics set, it is a game of mechanics which you could see back in the 90s and 2000s, which was quite popular, right? But the robot was built with so many parts and it was all autonomous. So the goal here was to build a few robots which may not be super useful to the community, but to build a robotic system which was autonomous. So there was a lot of passion flowing into building some interesting components into the robotics. Cybernetics was a discipline that was created late in 1940s by Norbert Wiener, combining feedback control theory. So feedback, as we all know, is a very important aspect of robotics. One part is the robot keeps on doing something what it is instructed for. And feedback is making sure that you know what you're doing and you're optimizing your system based on it. So where does feedback come in? Let's say I need to pick this cup using a robotic arm. So the robotic arm may have been positioned to come closer to this cup, but may not have been able to reach this cup. Feedback tells it through the sensing system that it needs to come closer, grasp the cup, and now it is ready to go. So this feedback control theory was for the very first time introduced by Norbert Wiener. Information sciences is in biology to try to explain the common principles of control and communications in both animals and machines. So many of the inspiration in this field was through animals and machines. So cybernetics, which many of us may be aware of, this terminology was coined in 1940. Okay, let's look further. 1950s, computer technological advancements and control machinery was developed. So this was getting more and more popular. 1954, the first silicon transistor was produced by Texas Instruments, right? That changed the realm of the computer systems and how we would see them right now in the day, right? 1954, George Devol replaced the slave manipulator in a teleoperator with the programmability of a CNC controller, thus creating the first industrial robot. So the first industrial robot was created in 1954 by George Devol. And he's sitting with this robot right next to him. Yeah. And this is known as a programmable article transfer device, PATD, right? So the goal of this robot was clearly to transfer articles from one location to another, or packages, or any kind of job or object from one location to another. So that was the initial goal for George Devol. And this invention completely transformed the industry. It created an industrial revolution, how robotics and automation has taken over the market in most of the segments, right? 1954. 1955, more interesting trends. The Dartmouth Summer Research Conference marks the birth of AI. This is your artificial intelligence. This took birth not right now, not 10 or 15 years or 20 years before, but back in 1955. It was not popular for many years, or did not find a lot of use for several different years, got very popular in recent times, but the birth was in 1955. Marvin Minsky from the AI lab at MIT, which is the Massachusetts Institute of Technology, defines an intelligent machine as the one that would tend to build up within itself an abstract model of the environment in which it is placed, right? So this is the first time a machine is trying to work in an environment, in an unstructured environment. If it were given a problem, it could first explore solutions within the internal abstract model of the environment and then attempt external experiments. So what the goal of the AI was to do was try different permutations and combinations of doing a certain things, whether the robotic arm should move like this, whether it should move like this, whether it should move like this. There are so many permutations and combinations, and finally figuring out through the model training what works the best. So this approach, of course, dominated the robotics research for the next 30 years and so forth, right? So if you look at the folks like on the background, like you're looking at this Dartmouth Summer Research Conference, these folks were quite old by that time, so I would assume most of them are gone, right? They are not there, but that's the birth of AI, right? 1956, researchers aims to combine perceptual and problem-solving capabilities using computers, camera, and touch sensors. So this was the first time everybody started talking about sensing, cameras, vision systems, computers, how they can play an important role in robotics. The idea was to study the types of intelligent actions these robots are capable of. A new discipline was born, which is known as AI in the modern world, right? So this is the Dartmouth Summer Research Project on Artificial Intelligence, and you could see the date. So this building was found during 1956, which is the first use of the term artificial intelligence, founding of AI as a research discipline, 1956, right? Interesting fact. 1956, a lot of things started happening. Joseph Engelberg, a Colombian physicist, Columbia physicist. Columbia is one of the top Ivy League colleges, by the way, in the US. So this physics student buys the rights to Devol Robotics and founds the Unimission Company. Unimission Company is one of the most popular company into the robotic arm technology. So 1956, George Devol applied for a patent for the first programmable robot known as Unimate, right? So this was well understood that he had created a robotic arm or systems which are going to revolutionize the next 50 or 100 years to come into the area of robotics and automation. So he well understood that fact, and he had to apply for a patent because there could be a lot of competition and stealing of his ideas. 1957 was followed by the launch of the first artificial satellite, Sputnik 1, right? Why is this useful? What has robotics to do with the first artificial satellite? The goal was space technology became very popular during this time frame where a lot of robotic systems got developed due to advancement in the space technologies, right? So the involvement of space technologies and complexities which are required there, because of course you cannot just deploy a person along with the space technology. A lot of things have to be automatic or launch in space. So a lot of these robotic technologies saw the light of, different kinds of advancement during with the space technologies. 1960s, you're looking at industrial robots which were created. So the Robotics Industries Association stated that an industrial robot is a reprogrammable, which can be programmed again and again in different sense and ways, right? Multifunctional manipulator designed to move materials, parts, tools, or specialized devices through variable program motions to perform a variety of tasks. This is a long definition. Long story short, what does it mean? It is a robotic device which is able to be programmed in any type of way with the goal of moving either a material or performing certain operations, like you can see on the picture on the right. So can this robotic arm, which is trying to maybe do a welding or some kind of, wire harness, which it is trying to put together, maybe do a soldering operation, can it be used for also painting? Yes. All you have to do is reprogram it. Reprogram it in a sense that you please start painting. These are the spray durations. These are the spray speeds, density. All these things can be controlled. So it's material handling, or if some component of the assembly of the automotive has to be picked from one place to another, right? So these were the industrial robots, and the robotic arm was created with this notion, right? 1960. 1961, the first Unimate robot was installed in Trenton, New Jersey, General Motor plants to tend a die casting machine. The key was the reprogrammability and retooling of the machine to perform different tasks. So this was first inducted in the General Motors plant in US. And the goal was to reprogram it, use it for different tasks, and try and test how can it do. Can it do anything better than the humans? The Unimate robot was an innovative mechanical device designed based on a multi-degree of freedom cantilever system. Of course, it's a multi-degree of freedom. This can go in so many directions. The beam flexibility presented challenges for control. So hydraulic actuations were eventually used to alleviate precision problems. So there were certain problems which were faced with precision and the beam bending or flexibility, then hydraulic actuation systems were included. 1962 to 1963, the introduction of the sensors was first seen as a way to enhance the operation of robots. So before 1962, there was no mention of sensors. Nobody knew that we would need sensors. But this was the first time the world of robotics, recognized that we need some sort of sensing mechanism to make sure that we know what kind of actuation systems or what kind of final operations needs to be performed by the robot. So the robot should not just be like, I give 5 programming steps and it performs that, but it should also be able to sense certain things and take certain, operations by itself. This included force sensing for stacking blocks. This is typically the step 1, that stacking certain blocks, what kind of force sensing is needed, like to understand the weight. Based on that, the forces can be controlled, right? Vision system for binary decision for presence of obstacles in the environment, which is McCarthy in 1963. Pressure sensors for grasping, Timovic and Bonney in 1962. Robot interaction with an unstructured environment at MIT's AI lab, Man and Computer project, which is known as the MAC project. So they were way ahead of time. If you look at some of these top universities in the world, like MIT, there is a reason they're the top universities, because they have looked at problems where the world was not even thinking about it. They looked at it from a next 50 or 100 years perspective. When the entire world was just focused on working on what is in the present time, they were looking at things, sensors, interesting aspects like working of a robot in an unstructured environment, because they could predict that robots are not going to only be industrial and performing certain operations. Eventually, they are going to be operating along with us, along with humans. So they were preparing for that from that point of time. And that's how, with that preparation, if you want to build a robot which is much closer to the human systems, what do we human systems have? We can sense, we have sensory organs, like we have the sense of touch, smell, you know, seeing, visual, sensing, hearing. So these are some of the smells which, some of the kind of senses which we have. So the similar set of sensors were created, right? Force sensing, probably the sense of touch. You have a vision system or a camera-based system that's like giving eyes to the robot. So now, while looking at something or touching something, can the robot function in a certain way? This was the next realm of possibilities. If you look at the evolution of sensors over the time, let's look at the plot or the timeline on the right bottom. The top picture shows the Unimate robot, which is used in the General Motors plant, more as an industrial robot. And the bottom picture shows the evolution of sensors over time. So most of it has happened from 1965. Before that, of course, the term sensor did not exist. Nobody knew what it was. So 65 to 1970, go all the way up till 1990. You're majorly looking at analog sensors, right? So digital computers, digital sensing, all these things came after the 1990s, right? So 1990s and so forth, and many of these sensors were built out of not only some of these research components, but out of defense technologies and space technologies, which needed these kind of sensing elements. Okay, let's look at 1965. Gordon E. Moore introduces the concept of Moore's law, which predicts that the number of components on a single chip would double every 2 years. So as per the Moore's law, an observation was that the number of transistors on a microchip roughly doubles every 2 years, whereas its cost is halved over the same time frame. Very interesting time. So we are looking at that the number of transistors or number of systems like or chips, like they double up every year and the cost goes down. And if you look at the computers, how they have evolved over time, this is exactly what has happened. The number of components have gone up, the prices have gone down. There were huge computers from where we started, like even taking a little bit of data, we needed floppy drives, cassettes, and whatnot. Then came the era of the desktops, laptops, and now everything is on that phone. 90% of your job can be done within the phone. So that was the concept of the Moore's law, which got popular in 1965, and it has driven a lot of evolution into the history of robotics. 1966 to 68, Shaky, which was a mobile robot, was developed by the Stanford Research Institute, which is again the #2 institute in the US. This was capable of planning, route finding, and moving objects. So all your line following and planning and things like that started back in 1966, right? It was placed in a special room with a specially colored objects. A vision system was used to recognize the objects and pushed objects according to a plan. This planning software was known as TRIPS, and it maintained and updated a world model. It could not only do the mapping, it could also sense that what kind of decisions it has to take if it sees an obstacle, if it sees certain colors, what kind of organization, reorganizations have to happen. The robot had a pan, tilt, and focus for the camera and bump sensors. 1966 only these kind of robots were built. Right? 1968, Kawasaki Heavy Industries in Japan acquires a license for Unimate. So Kawasaki Heavy Industries, most of us are well aware of, they're into the automotive segment. So they acquired a license in Japan for Unimate because Unimate became very, very popular. Unimate was basically redefining how industrial robots would look into it, right? Because they are in most places going to take up most of the jobs of, into the automotive sector. Typically, it started from the automotive sector, the Unimate or the robotic arm, which is known per se, so they are going to pick up things from one location to another, perform operations like welding, soldering, painting, and things like that. Around this time frame, 1969 is when the Apollo 11 mission puts the first man on moon. Landing was made inside the lunar module Eagle, and you can well imagine there are a lot of automatic components, robotic components which were built around it. So there was a lot of interest across the countries, and everybody wanted to land the first man on the moon. They wanted to go hit the space, right? So a lot of the technologies in the 1970s were focused around space technologies. Luna 17 landed on the moon carrying the roving remote control robot, which is known as Lunokhod 1. Right? So a lot of robots were built around that time frame, which revolutionized how robots would look like. 1971, Intel introduced the first commercially available microprocessor, the 4004. 1971 to 73, the Stanford ARM was developed along with the first language for programming robots, which was known as Wave. So we have so many languages for programming the robot, but one of the first languages was Wave, right? 1972, another interesting area. The first snake-like robot, which is known as the ACM-3 Heros by the Tokyo Institute of Technology, was built. So this was inspired from the snake's movement and its joints. And this is the picture, the second picture in the middle, the set of pictures. So inspired from this snake, look at this system. What does it look like? Can you identify this with any of the robots which we have in today's date? It just looks like an endoscope, right? So if somebody has a stomach ulcer, somebody has some problems in their stomach, these kind of robotic technologies have basically been taken from a bio-inspired system like a snake, where there can be so many joints, where of course these maneuvering through so many obstacles within the human body might be very, very challenging. So the original idea was not to build an endoscope. Original idea was to build something which is bio-inspired, but that ended up bringing that technology into the medical realm. So that being said, a lot of the technologies may have been built for some other purpose, but how they are being used currently in another discipline may have just adopted some of these technologies directly rather than them having to build everything from scratch, right? Then in 1970s, JPL deploys its first planetary exploration rover using a TV camera, laser rangefinder, and tactile sensors, right? 1975, the space probes Viking 1 and 2 were launched, each with an articulated robotic arm. So the reason we are talking about space technologies is all of them had some robotic components, right? Either to collect data, collect some samples, or do certain operations. So there were so many interesting attributes. 1976, the film Star Wars was released, introducing R2D2 and C3PO. So how is this relevant, the film Star Wars? Because like I said, how the robot term has been coined from a play back in Czech Republic, many of the films actually had an adaptation of what was going around that in that time frame, as well as what the humans can ambitiously think of. Like, for example, if somebody thought about the flying cars or flying systems, that's there right now. Those are the drones, for example. Somebody has envisioned about the computer way before the computers were actually there. So most of these movies had some ambitious components and some components which were there happening around that time frame. So the Star Wars movie got very popular because most of the focus of the countries around that time was to get into the space, build robotic technologies which can go into the space. And that is what these movies were about, right? 1977, the development of mobile robot Hilaire at Lab of Automatic Analysis Systems, like LAAS. This is just a different pronunciation. In Toulouse, France. So this is given in French. This mobile robot had 3 wheels and it was still in use. It is still in use, right? This was created during 1977. Okay, looking further, 2 famous robots around this time frame. 1978, Puma, which is known as the Programmable Universal Machine for Assembly. What does it look similar to? It's similar to the Unimate. It's just a different version of it, much more optimized version of it by Unimation, right? This became very, very popular. 1979, the SCARA robot, which I was talking about, which is a selective compliant articulated robot for assembly, right? First got introduced in Japan and the US by Adept Technologies, right? You could look at the SCARA robot on the right side, the blue one, right? So this became very popular. Why did it get popular? Because the industry needed it. So one thing we should always keep in mind is whatever is happening around the world in terms of technology, it's always driven by demand. Things do not happen like overnight. AI is there because there is demand. Robotics is coming along because there is demand, right? So all these things are driven by demand. So that was the similar setting back in 1979 also. Many of the companies wanted to go big on cars, big on assemblies, which they could not get through the manpower. Manpower could fatigue after 7-8 hours. They cannot give the same amount of precision, same amount of detailing. That's where the robots can be doing that. So that's where the SCARA robot was introduced. 1980s, there was more innovation in improving the performance of the robotic arms. So most of the robotic arms were quite well realized by then. So there has not been a huge like shift in the robotics arms in the last 40-45 years, like we are at 2025. Nothing much has happened into the robotic arm realm except the performance enhancement. That has been the entire goal. So the robot structure and all the assembly components were quite well understood. But the next step of things were how to improve the performance. Can we have a feedback control? Can it have a precision movement for some surgical practice and things like that? So that was the goal. So feedback control, like I said, to improve the accuracy, program compliance, the introduction of personal computers such as controllers, and commercialization of robots by a large number of companies. So very interesting, around 1980s, everybody wanted to take a piece of the cake, right? What was the cake? It was the robotic arms. So I'll just give you an example. 3 years back, three or 3.5 years back, when we had the COVID pandemic, what happened? There was an entire lockdown. Every industry got shut down almost. What was everybody developing? What were all the companies making? Personal protection equipment, typically the masks, right? So we had a huge mask shortage, if you remember, like in the initial phase of the COVID 2020. Then all of a sudden, every company, be it a shirt company, be it an industrial company, be it a street vendor, everybody started jumping into mask production, and within a few months, we were exporting masks, right? The reason I give this example is in 1980s, something very similar happened. Every company wanted to jump into getting some robotic arms because they thought this was the new thing. This could enhance the production of their particular companies. This could completely transform how their companies function. So KUKA robot, IBM 7535, Adept robot, Hitachi, Seiko Corporation. Seiko Corporation was originally a watch company, right? Like, so they also jumped into robots. So many of the companies which were originally not into robotics, they also started jumping into robotics, that I want to have something at least out of that. Early in 1980s, multi-fingered hand robots were developed by the Utah MIT arm, 16 degrees of freedom. Very preliminary. Of course, the robotic arms which you see right now may have nice finger movements and things like that, but the 16 degrees of freedom was developed by Steve Jacobson, by Salisbury Hand, which is with the 9 degrees of freedom. So many of these robotic arm technologies started becoming popular. This was the new trend in the market that everybody wanted to build. Now that this robotic arm overall was built, what about the end of the robotic arm? Can it do a grasping function? Can it have some functionalities which are just like the human arm? So that was the goal. So one trend to observe is always robots have seen, can we become like the humans? The robotic technologies have always seen, can we become like the humans, but a much more efficient and full performance human. So that has been the ideology for most of the robotics. Well, right? 1977 to 83, we are looking at a Stanford CART CMU rover, CMU's Carnegie Mellon University, right? Developed by Hans Moravec, later on becoming the Nomad mobile robot. So what are some common universities which you see here? All the top-notch universities, like in Japan, Tokyo University. In US, you have looked at MIT, Stanford, CMU. And this is the reason why these institutes are so popular for robotics, right? If you ever want to study or do a higher kind of thing, they have a legacy of robotics because they started certain things way before time, when people did not even imagine how the market is going to look like, right? 1980s, all of a sudden there was a switch in the system. It was not only robotic arm, people started jumping into the market of legged and hopping robots. Right? What is a legged and hopping robots? All of a sudden there was this huge thing. Can we, now that we have replaced or made an arm similar to the humans, can we have the lower extremity, which is everything from your hip down? Can we replicate that system, like with all the joints in the humans, and also have it function? So there were a lot of issues, like initially the human gait means like the style of walking, right? It has certain phases, like you first strike your heel on the ground, then there is a weight shifting, there's a stance phase when your feet is in touch with the ground, and finally you have a toe off, and after that the swing phase starts. So there are certain steps of your gait which makes sure that you are able to stably walk. Like a toddler or somebody, let's talk about a baby of a year and a half, they're not able to walk. Why are they not able to walk? Because their walking pattern is not proper. Similar with the robots, if you're trying to build a robot, you have to make sure you optimize all the balancing parameters, all the different joints are properly aligned just like the humans, and they have to be tested in order to get the gait or the walking parameter right. So that was the goal shift in 1980s. 1984 to 1991, you're looking at something more. V. Breitenberg revived the tortoise mobile robot of W. Gray Walter, creating autonomous robots exhibiting behavior. So this was the first time we started talking about behavioral robotics. Hogg, Martens, and Resnick at MIT again created mobile robots using Lego blocks. So what does Lego blocks do? Lego blocks are your normal building blocks, which we all played with like 20 years back or 15 years back, maybe. They're still in the market. Lego is quite popular. So Lego came into the robotics system using Lego blocks. They have used this into behavioral robots. Rodney Brooks at MIT creates the first insect robot at MIT AI lab, which brought the birth of behavioral robotics. Look at this insect robot for a second and just think about what technology did it end up into. The drone technology. So these kind of bio-inspired system, how a insect or how a fly can actually fly, that eventually led us to the drones. It is not like somebody just woke up and said, like, let's put 5 different, like, wings and this is going to fly perfectly. No, never happens like that. It is all bio-inspired, right? Again, MIT. So they have done something where drone technologies, if you look into the market in India, they have become popular in the last 10 years, I would say, 10, 15 years. But you're looking at 1984, which is almost 40 years from now, when the technology was there, right? So the divide is decreasing, but slowly and slowly we are seeing whatever is happening first in the West. Some of the top universities are slowly getting adopted in the rest of the world, right? Okay, now the goal was, one was the drone technology at its infancy. Second was there were certain attributes of the humans which the robotic companies were trying to replace, like the lower part of the body, because that's the most important. The upper part is still easy. It doesn't have to do a lot. The lower part gives the balance. It has the walking attribute, and that drives your body. So a robot will not be able to move unless you get the lower part right. So 1986, Honda started its work on the first humanoid robot, which is known as robot named E1, later to be named as Asimo. I'm sure many of you know what Asimo is, right? Around 1990s or 2000, Asimo was a very popular robot. This came in the Delhi Science Center. There are so many places where all the trade shows, conferences was bringing Asimo. Everyone wanted to take a glimpse of Asimo. This was the first humanoid robot. The story it tells you is, now the goal of the researchers, role of the industries, where now that we have been able to develop a lot of different robots, robotic arm, industrial things are okay. We have started developing the bottom part of the human body. Now can we build the entire human? Ambitions never stop, right? Like always there is a goalpost which keeps on moving. So 86, the idea shifted to, now that we have done a lot in robots, the sensors are in place, vision systems are in place, can we build the humanoids? Can we build models which are just behaving like the humans? 1988, Scam designed the first robotic pet with emotions. So there was a lot of focus on the behavioral robotics as well. Mark Tilden introduced the BEAM robotics, BEAM being an acronym for biology, electronics, aesthetics, and mechanics, right? So many of the bio-inspired systems became popular during this timeline, one of that being the drone technology. 90s, modifiable robots for assembly, mobile autonomous robots, vision control robots. So vision control and all these systems came into the system. Walking robots. Walking was perfected within just 5 years time frame, right? With all the right amount of actuation, right kind of loading, balancing, and everything, humans were able to make the walking perfect in a robot. With all the joints, they were able to walk properly. 1991, the first HelpMate mobile autonomous robot was used in the hospital. So this was another robot in that same time frame. Okay, 1990 is where the actual era of humanoid started. Here, every company wanted to now jump into the area of humanoid. Like every company wanted to jump back in the 60s into the robotic arm to get an edge in the industry. Now in 1990s, the story just shifted, just less than 20 years, and everybody wanted to build a humanoid now, right? It's a rat race all around the globe, right? Cog, Kismet, MIT, Wasibot, WHL1 by Japan, Honda P2, P3, Asimo, these were all getting into the market, and because the bottom part of the body was okay, part of the body was well simulated by robotics. Now all everybody wanted to do was build the top part in different parts and like roll out a humanoid. Right? So the humanoid research became very, very popular. 1990s entertainment and educational robots, which is known as Sarcos, which you can see in the Jurassic Park, Sony Abo, Lego Mindstorms, Kepera, Parallax. These ones became really, really popular. Right? RoboCup is a competition that simulates the game of soccer played by two teams of robots, have been held around like since 1997 in Osaka, right? So why would you need robots to play, football? What's the big deal about it? Like, would humans not play the football? Like, why would you need robots to play it? So the idea was to just push the limits. The idea was not to create something which is immediately worthwhile or immediately useful for the society. The ambitions were that, can we build something where it's behaving like the humans and it is able to do certain activities which uses the brain, or some systems, vision systems in this case. You see something and you make certain tweaks and turns to your movements. So this RoboCup became very, very popular. Many of you may have heard about this RoboCup, right? Okay, 1997, Sojourner becomes the first robot to land on Mars as a part of the Mars Pathfinder mission. The reason I jump from humanoids to few other things which are happening during that timeline is because these timelines are very important. When what has happened, that has influenced a lot into the robotics market. 1998, Lego enters into the robotics market. Lego realized that they were being used in many places for building robotic systems, and they, being a completely building block company, toy industry, wanted to get into robotics with their first version as Lego Mindstorms. 1999, Sony introduced Abo, an autonomous robotic dog capable of seeing, walking, and interacting with the environment. This was followed by a year later by the SDR-3X humanoid robot, later on known as QRIO. These both have been discontinued in 2006 with better robotic models, right? So 90s saw a lot of growth of humanoid robots. Many of us may not be aware of that, because humanoids We can hear some of the stories now in 2024 or 25, but the research and the actual building phase was almost 20 years back, 25 years back. So this is how the entire shift happens. And this is exactly what I was talking about in the terms of job market and what is going on in the market, right? So we may not realize how much robots or robotic systems are penetrating even in the Indian market, unless we look at the finer details, like talk with the industries or see what exactly is going on there. By the time we are skilled, we are in the right position to get into this market. But somebody who is not skilled, another 15, 20 years, it is going to be fully robotics and automation in majority of the industries. In India, are we building any humanoids? I'll get to that point in the upcoming, slides. So 1990s, more thing happened. Introduction of space robots like rovers, Mars rovers, multiple manipulators, precision robots, surgical robots, first service robots. Many of these things got popular and commercialized during the 1990s. So the surgical robots did not come 5 or 10 years back. They were built first time around the 1990s. 2000s, Honda unveiled the Asimo, the first non-prototype release of the humanoid robot. 2001, US Air Force tested the MQ-1 Predator, the first unmanned aerial vehicle UAV fitted with 2 Hellfire missiles. Like, how is this important? Because these had some robotic technologies during that time frame where defense was getting more and more into this robots, right? 2000, iRobot introduced the first autonomous vacuum, Roomba, which now we have seen into the consumer market as one of the top playing robots into the consumer market. So this was introduced back in 2000 when nobody paid attention to it, right? Just 20 years down the line, this is in almost every household in the West. And this is getting more and more popular in the Indian context as well. I have seen many people, many colleagues who are fed up of the maids and household workers. They have taken a vacuum cleaner of this sort, iRobot, Roomba style. There are so many brands in the market. They've brought one, they're cleaning up things, right? So this is getting quite popular. 2000s mini and micro robots, Smart Dust, Pister at Berkeley University, UTA, EPFL, Luzern, micro factories were built. So lots of micro systems were built which were focused on, like, building smaller robots, congested robots, like, complex computer systems. So that was one of the goals back in the 2000s. Like, this is where you probably remember the Y2K generation, where there was so much shift towards the computer systems. 2000s, lots of military applications came into the forefront. So robotic assistants for dangerous environments and reconnaissance, AUVs and UUVs became very, very popular. So defense started adopting and looking into the robotics back in 2000. That's how the defense market started evolving into robotics. 2000, another interesting thing happened. Intuitive Surgical introduced the first Da Vinci surgical robot. Still to date, Da Vinci surgical robot or its adaptation is what is used in majority of the surgeries, right? This was back in 2000, but the technology became popular in the last 4 or 5 years, where if you go to a hospital for a surgery, most likely than not, you will get an option of either a normal regular surgery or a robotic surgery, which is typically twice the cost, right? Many are opting for a robotic surgery due to high precision. They may not have a high trust for the doctors, right? And there are so many other attributes which are there. 2000s also, there was this robotic deployment of sensor networks, right? So which was another popular milestone. 2002, iRobot introduced Roomba, like I said, which is a personal robotic vacuum cleaner, was quite popular. Osaka University unveiled the first Actroid, the term given to humanoid robot with strong visual human characteristics. So the earlier goal, if you remember, was to get the gait correct, the movement correct, build something on top of it. But now the goal had shifted again. In 2000s, everybody became ambitious and they were like, can we build robots which are exactly human looking? And if you remember most of the movies during this time frame, 2000 movies, around the year 2000. Many of them were focused towards robots which were human looking. Like even if you look at the later versions of the Terminator movies, or there are so many movies which are coming in different languages, like, they had some robotic component into it. Many of those movies got popular recently, but the movies also give more ambition to the industry that this is what we would desire, right? 2004, the first DARPA Grand Challenge happened. What is a DARPA Grand Challenge? DARPA is a very interesting and important milestone in the US, where lots of student teams built technologies through a grand challenge for the defense. And these student teams do fantastic job. Many of these technologies are transferred to the defense using the DARPA Grand Challenge. They have this open every year typically. So this is sponsored by the US Department of Defense. The challenge is designed to create an autonomous vehicle for warfare. So the focus at that time was autonomous vehicles for warfare, right? Robotic systems through students. So 2004 saw a lot of defense applications which are moving into the robotics. 2004 again, the Mars rover Spirit and Opportunity landed on Mars. So this was the first time we were looking at Mars. So everybody is getting more and more ambitious, right? So the ambition is what drives most of the sectors, right? If you look at it, it's need, and it's creating that artificial need, which creates the ambition, right? Like that, this is what we want to see in the future. As of November 2009, the Land Rover has completed 2150 days of 92-day mission. 2010, NASA and General Motors joins forces to develop Robonaut, the new versions of NASA's humanoid robot astronaut. Another interesting phase, 2011 to 24. Very interestingly, the robots have not seen a lot of hardware transformation. The focus mostly has come into the robotics and automation and incorporating that into majority of the industries. So as we speak, like I said, this revolution has already started around 2011. So we are almost 14 years into the system. You give another 7 or 8 years, the industries are going to look extremely automated, right? So that gives us a very rich market right now to grab jobs into the robotic systems, get skilled, reskilled, get some ideas on how to build robots, probably build startups which can get very, very popular in the segments where the market actually needs it. You talk about most of the segments, most of them have a dearth of, robotics, which is there, right? So hopefully this things gave you an insight on, like, which areas the robotics have evolved and how they can be tuned in your own perspective, right? Focus has also shifted towards application of AI and ML, which is all of us are well aware of, that AI in robotics or ML in robotics is a new thing, right? Like we want to make sure that the robot is able to collaboratively do attributes like which it cannot do in its own functioning, right? Like it is able to learn from its environment and work along with the humans. Humanoid development is another area of interest which has peaked up like anything. Every year, at least 8 to 10 models of humanoids are getting created by all the countries enforcing their defense mechanisms and things like that. Surgical robot manufacturing is another area where more and more improvisation into how to do a precision surgery has been an area of interest, right? So given that, I told you that I'll tell you about, what kind of humanoids are getting developed in India. Is there any research going on? Yes, the answer is a yes, but in stealth. So I work with some of the DRDO labs, few of the very top labs into ballistics and other things. Like, so they are preparing some humanoids underground. That is what we have seen. Like there are humanoid technologies which India is also developing, but nobody wants to talk about it because it's going to be like the missile technology typically. So it's going to be something which is going to change the realm of defense very much at the borders, right? So think about an army coming to capture a certain territory, and there is a full army of humanoids waiting for them with all the fixtures who can fight 24/7 just ready to be captured, right? And also not only that, having an entire industry replaced by humanoids where there are some very skilled people like us, like who are able to operate with these humanoids and work with certain programmings, repair those humanoids, give them certain tips and attributes that how to function within that environment. So that kind of a skilling and reskilling is happening over the years, right? So that is what I wanted to talk about, so hopefully you got an initial insights into what robotics is. This is just to bring everybody into the same page. Many of you may have some of this information already, but just to get you interested that this is the area of robotics, this is what has been happening over the years, and this is the future, right? And we will be staying tuned for a lot of very interesting lectures delving into the different realm of robotics in the coming hours and the coming days, and hopefully you will be learning a lot about these. So I'm just going to quickly take some of the questions. I'm sure many of you are interested to know the answers. So Joydeep, I'm sorry, I don't know which slide I left with, probably I missed it earlier. So yeah, so Amit is saying due to some technical issues, I was not able to log in through Times Pro, so I had to join the session through direct link. Just make sure my section is, yeah. So I would request Times Pro to kindly make sure that Amit, who has just written the message, that not to be marked absent, right? So if there is a link issue, I would request Amit and others, whosoever is facing that, to just reach out to Times Pro, and they should be able to, figure that out for you. So don't worry about the attendance part. We are well aware of that. There could be some initial issues which will streamline over time, right? Next is from Prashant. The intent behind robotics penetration seems to be reducing manpower. Yes, to some extent. From a more macroeconomic standpoint, isn't this a problem? Reduction in human labor and unemployment. Yeah, this is a very important question which has been raised by Prashant, because population is increasing, and if the tools of reduction of employment gets more widespread, do you see an issue here? Maybe a philosophical debate, but isn't it an important one? So I think this is a very important question for all of us, and I think we would love to get some answers. So this is what I've found out from the industry. I'll tell you that fact. So the idea is not about only reducing manpower. The idea is about reducing redundant manpower. So the keyword here is redundant. Manpower which is focused on just doing the same job again and again, and they are not adding any innovative value to the system. They are the ones who are going to most likely get replaced. And so that these people do not get replaced, they have to get skilled in certain areas which are unique, like could be AI, machine learning, could be in the area of robotics, where they can build something innovative. So the focus has been towards innovation and creativity. If you look at the broader markets, every industry, even in India right now, if they get a chance, they would want to take away all the redundant people into the shop floor, into the different assembly lines, even if it's 10, 20, 30, 40, just multiply it with the number of their salary, give that to a robotics company, be it a startup or an industry who can develop robotics to replace those operations. This is actually not a problem. This puts us in a nice place. It's a restructuring where a lot of us, if we get skilled in the hardcore robotics field, not only robotics as a software, but robotics where we can build, uh, you know, train with robotics, innovate with robotics, repair them, can actually fit in these positions for a much more higher salary. So it's a restructuring of the industry rather than a reduction in the jobs per se. So the skilled is going to get higher pay with higher chances of jobs in a lot of industries. Think about, let's say there are 1,000 industries which have never adopted robotics and automation, and they would need, let's say, 5 or 10 people each for taking care of the automation and robotics in their industry. So you have 5,000 jobs directly which are newly created, but these are skilled jobs. But what they're getting away with is like some of the redundant jobs. So that's the theory of things. More skilled jobs are going to see the light of the day, and the redundant jobs are going to be lost, right? So hopefully that makes sense. So the next question is, one of my close persons, he's looking for humanoid robot to perform in his film. We are looking for the solutions. So yeah, so I don't know if I can answer that. I'm the right person for that or not. So there are a lot of humanoid robots which you can source out of China. I don't know the exact names what you could use in your film and what may be useful. But we are happy to look at it. If you need some recommendations, we can look at that, but it will be easier for you to source from China and probably use it, like because they are building it in huge bulk for now, right? Next is Prashant, do you think statistically robotics adoption is inversely proportional to the population volume? South Korea is a small nation with low density, but with a large production volume to deal with. India, the Americas, or Mexico, for example, your comments on this. So, Prashant, just an extension, this is more of an extension of your question. So, I think what I would say is, I would not attach any proportional value to it. I would rather say wherever you have a large amount of manufacturing volume involved, that is where you are going to see this higher penetration of robotics very, very clearly. Because like I said, the redundant jobs, everybody in the higher management is keen on taking away because of multiple reasons. It's not to not pay salaries to people, because they are not able to perform 24/7. That's the idea. Everybody is focused on enhancing their performance. So if, in an automotive sector or in a surgical robotics sector, if somebody is able to, for example, produce their goods 24/7, 7 days a week, they would rather prefer that rather than having people change their shifts every 8 hours and paying them that much amount of salary. Robotics is more of a one-time investment where they can keep on going. So that is what is happening overall. Wherever you see a lot of manufacturing, lot of operations which is redundant labor, so like packaging, some sort of like systems which are placed from here to here, all kinds of redundant jobs, difficult to do jobs like welding, soldering, these kind of things which can be easily handled by a robot, they are changing hands with robots typically. So that is my take based on the industry statistics, and that is irrespective of the country where the focus is. So if certain countries are not focused on manufacturing, you will not see a lot of robotics in there. Countries like, I would say, UK, you don't have a lot of manufacturing. Australia, maybe. Some parts in the US doesn't do a lot of heavy manufacturing. So you may not see a huge penetration of robotics, even though they're embracing robotics so much, right? China, India, which are, manufacturing hubs like South Korea, these are places where you are going to see a lot of these robotics. These are the hotbeds, like probably not that much in Singapore, maybe, because they are not focused on manufacturing, right? So hopefully that makes sense. Pick and place robots, like I said, is like, typically the ones which can very quick and precision pick something as small as like, pills or drugs or certain, components within a drug chamber, like, and put it for a control, put it for a test. So what happens in the pharma industry is typically, let's say it's a paracetamol industry. So you have hundreds and thousands of paracetamol tablets which are coming in, right? So there are some quality control measures. So these robots, what they will do is they will randomly pick, let's say, 100 tablets out of it. And then there are some control steps that they need to be dipped in a certain chemical or tested in a certain way, that how solid they are, how much is their overall content and things like that. So this is what the pick and place robots are quite popular. Right? Another pick and place common things, if you're looking at packaging industry, this is more of a thing like you pick from here, place it here. That is where there is a bin which is going to go and ship. So these are the pick and place robots. So there are a lot of applications which are of interest. Next is, yes, which can be used under palletizing and packaging. Yeah, you are correct. Assembly, screen testing, dog robots are getting popular in army. Yes, they are. Many of the dog robots are getting popular in the army because they have sensing systems and they can get through nooks and crannies, places where the humans or the humanoids cannot go through. Yeah, Cold Wars, yes, but it could also end up in like pretty, difficult war-like situation in many countries, what they're trying to develop, so I don't know the question about decision making, so I'm going to jump from here. How AI and robotic technologies have been developed from 1955 in spite of not having the same pace of development in computer technologies as AI and robotics technologies need a lot of complex computer programming. Yeah, I think you've answered the question yourself. Like most of the AI and robotic technologies, even though the terms were coined, like, some development or research happened back in 1955, but unless the digitalization happened where everything went from analog to digital computers came in, most of the volume of data could not be processed. And that is one of the reasons that AI and robotics became very popular, not robotics per se, like AI ML became very popular into the system once you had very small computers and computers were in everybody's hands, right? Where earlier computer was more of a luxury, where it could be in a certain industry. But right now everybody is with a laptop or a mobile phone. You could have computers in every places. So that's how these technologies have really seen a boom over the time. And they did not see a lot of boom in those eras. Hopefully that makes sense, right? RoboCup was fully automotive or collaborative. So RoboCup, I would say it was quite collaborative because you are looking at a very unstructured environment where you do not know how the other robot may come in, where exactly what kind of movements may the other robot make, right? So this was highly collaborative, and this had a lot of effect of the vision system, how it looked at it, what kind of actuation systems did it trigger, right? So yeah. Do you have a class tomorrow? The answer is a no. So I think we just have some projects after the 27th. So 27th is when we have the project kickoff. And after that, we will have some classes, project sessions on the Sundays. So you do not have a regular teaching or lecture session on any of the Sundays. So that's the answer. Redundant and manpower is prone to risk. That is correct. Yeah, Mohit, I think the same answer is here. Next is Nitin. His question is, why hasn't India been able to develop companies that manufacture industrial robotic arms at scale and sophistication of global leaders like ABB, Siemens, Yaskawa, or KUKA, right? During my experience in the industry, I have noticed a significant gap, particularly in the development and manufacturing of advanced motion controllers, which seems to be a major bottleneck. What's your say for this? So I would give you the answer for this, and I think this is question is really nice. This is informative for everybody. The answer to this is India has historically never focused on building hardcore robotics, like hardware-based robotics. If you look at majority of the Indian market, I would say like 3 or 4 years back, it is majorly built around softwares. That's why robotics has almost become like an area of computer science, because we are very good with softwares as a country, like where everybody is good in coding and they can deploy these softwares to any sort of applications, be it robotics in India and abroad. So that has been the typical focus. So we do not have a lot of skilled manpower who are able to actually build this robotic arms. That is number one. And second is, not a lot of companies are interested in doing this because this is really deep tech. But that interest is coming now that with the Make in India push, and now that we have realized the import duties are huge. If you want to purchase a robotic arm from abroad, you're probably looking at crores of funds. So creating the same kind of technology in India, you can probably create 10 to 50 of those within that price. So that is where that dearth is now being seen, and the many of the companies are basically taking that stride of building this robotic knowledge, but that skilled manpower is very required. And that was one of the key purpose of this course. If you look at, we wanted to skill and reskill people in robotics, hardware based robotics as well. Of course, there is a component of software where we are able to solve the next problems of the nation, right? Which is into the shortage of building robots. We are able to create certain startups where we can create things in the global, like the global leaders. So that's the idea, right? Hopefully that clarifies that. Next is Adam. I think the question is, I think manpower cost also is a factor, that is that it is cheaper to get 10 manpower than one robot. Yes and no, I would say. Redundant manpower cost is actually going pretty high if you look at it. So earlier you could, so back in the day, I will tell you from a fact and figure standpoint. 2010, I'm standing in Tata Motors plant in Lucknow, right, which is the bus manufacturing plant in Lucknow. And I'm telling this from a observation, like in a particular stage of the assembly line, there are 8 to 10 people, each one of them drawing a 5,000 rupee salary. So let's say there are 10 people. How much are we looking at? 50,000 rupee salary. That salary currently is close to 25 to 30,000 rupees per person. So you're looking at a 3 lakh. 3 lakh rupee, not for the assembly line, for a simple stage of the assembly line. Think about the entire assembly line, which has, let's say, How many? 20 stages, right? How much are you looking at? 3 times 2 and then times 10, 60 lakhs. 60 lakhs for running an assembly line. I could have a few robots, one-time investment, right? And change that entire assembly line with high performance. So that is where the equation is. Okay, next is Swadesh's question. How should we look at drones as a robot? So especially if it is being managed by humans by a remote instead of acting autonomously. Yeah, this is a good question. So if you look at drones, you would not call them like robots per se, like they cannot be if they're controlled by a human, but if they can perform certain functions automatically, there are many automatically moving drones which are able to, in defense application, maneuver certain places, take pictures when it is necessary. They are autonomous drones, complete autonomous robots. But in the definition of robots, if you remember, there were two definitions. They could be either externally controlled or they could be embedded control. So the focus has now shifted more towards embedded control, where drones can just fly on their own, have a certain path, find the necessary path, and can autonomously do that. So drones are slowly moving towards from just an electronic device to being a robot. So that transition is happening. So yeah. Next is, are there any examples where vehicle manufacturing industries have evolved beyond linear assembly line process into non-linear micro factories with help of robotics? Yeah, one example is your Tesla manufacturing plant. If you're looking at the manufacturing around the world, I'm saying, not specifically in India. Tesla is completely automated. Every step is automated. You have robotic arms like doing everything. Majority of the automotive sector in China doing the same. In India also, there are multiple robots which are getting sanctioned every day. Not the entire assembly line is changed into robotics because people are a little conscious about like changing everything or giving it in the hands of robotics, but they are happening in stages. So vehicle manufacturing is one of the earliest industries which is adopting into the robotics trend, right? Like the next question is Jagesh, like when calculators and computers came, old clerical jobs change. So industry and society will upscale eventually. Yeah, this is correct. Exactly the discussion which I shared, you know, how redundant jobs are going to be taken out. Upskilled and reskilled jobs are going to find higher value and salary. That is exactly what is going to happen. Unitree G1 humanoid about $16,000. Yeah. So $16,000. Yeah, thanks for sharing that insight. I did not know the price of this. So these are the price of humanoids. I'm sure we can build something much cheaper than this in India, right? With a higher quality. Can CMM be considered a Cartesian robots? I don't know the full form of CMM. So Agnesh Shekhar, like maybe I'll have to ask you. Coordinate measuring. Acha, this is coordinate measuring machine. Yeah, if you have a coordinate measuring machine, I don't know which specific machine you're referring to, but anything which is going by the coordinates and has an autonomous system in place, like a 3D printer, for example. It knows exactly where to go from here and where to go next, and it keeps on doing its job without any human intervention. So that is typically a Cartesian robot. Coordinate measuring machine, I'll have to look into what exactly this machine does, but if it does it automatically, it's definitely a Cartesian robot, right? CMMB, I mean coordinate measuring. Sorry, I'm repeating question. Probably it was overlooked above. Yeah. So yeah. So if you have sent an email to executive program, have you been able to see it? Yeah, Joydeep, I think we are about to gear that up. I think we just got the TAs on board and they are right now starting to send us the emails. So if you have sent us an email, thanks for the reminder. We will start looking at it from now on, right? So, and we will be responding to all of those like as it comes. So you can expect a response within the next 2 days or so. That's right. Yeah, you're welcome. Next is a CMM is a precision measuring device used in the manufacturing and engineering to measure the geometry of physical objects by sensing discrete points on the surface. Acha, it's a probing device. Okay, I see. Yeah, if it is automatically probing it, then it will be a Cartesian robot. Yeah, you're correct. Like if it is automatically probing it and it knows where it should move in order, how many places it has to probe without any manual intervention. Yes, Neil, it will be a Cartesian robot, considered to be a Cartesian. Yeah. So hopefully that brings us to the end of all the. Yeah, would it be possible to visit you at IIT Delhi campus? Want to discuss? Yeah, that's totally there. You guys are all students and the assets for us for this course. If you want to come to IIT Delhi, discuss any robotics project with us, it's a warm welcome to all of you, right? So you can always do that. Yeah. So hopefully this gave you the initial insights. So let us go for a break. I think we overshot on the time. We were supposed to have the break from 12 to 12:30. So what I'm going to do is some exceptional, yeah. So I don't know what this question is. Why restrict session on laptop? Some exceptional case may have to. Yeah, so I would request, that if you have any particular questions, feel free to write to us and the reason we do not give our numbers publicly because it's a lot of calls and emails where we may not be able to respond like directly, sometimes, and it may create a issue where somebody may feel, not very good about it. So that's typically the norm with most of the programs. I would just request you to shoot an email to our email address and we'll start responding to it. Like, be assured, please. Like, we'll respond to you with as soon as possible, right? And if you want to visit the campus, come in an offline mode, that is more than welcome, right? Yeah. All right. So thank you, everybody. I think that's a good start. Let us take a break. Let's reconvene at 12:40, right? So then I would just request Professor Vishwarup after that to start with his session at 12:40. So let's all reconvene at 12:40. Let's all take a break and we will see you again shortly, right? Thank you.
uh, Robotics.
Yes.
We'll
Yes, sir.
soon get started, and we're going to talk about the present and the future. Since you've already heard about the past,
Mhm.
we're going to talk about what the present status of robotics is.
Okay.
We're going to look at a lot of videos today. We're going to try
Mm.
and keep the first session a little bit light,
Yes.
and then we'll get into the weeds of it in the next class.
Okay. Okay, sir. That's fine. Thank you, sir.
Thank you. So, to all the students, while I'm presenting, I may not be able to attend to your chat, but please do put your questions. I would like the session to be interactive. So you will see that I'll ask you questions, and I would appreciate if you respond to those questions. And we'll try to, again, this is a fun session. We're trying to keep it fairly simple today. I mean, this is the first introductory class, so my aim will be to keep it light and keep it fun for you for the first class. So please feel free to ask any questions that you have in your mind. There are no questions that are stupid or anything of that sort, right? So please feel free. This is an inclusive learning environment. We want you to learn, go back home, and have a wealth of knowledge with you. Right? So do raise your hands before you start asking the questions. That I would appreciate that, and I'll definitely reach out to you and answer your questions. And if it's not a pressing question, you can always put it in the chat. I'm going to attend to it at the end of the session. So the way I'm going to talk about today's session is that we're going to have a first half of the session, if you will, where we're going to talk about a broad and a philosophical definition of robotics. I think you've already heard one definition of robotics from Arnab. Um, and since we share some expertise and we have other complementary expertise, I would like to give you what I feel is a more philosophical take on robotics. So we'll start with that theme. And then as we progress through the lectures, we're going to start seeing that we're going to get into sort of more technical details. And we'll look at the classification of robots in various broad categories, right? How do we look at robots from different angles? And we're going to make that interactive. We're going to try and answer some questions and try to clarify that when I look at a robot, instantly can I tell what kind of a robot it is. And understanding these terminologies that are very closely associated with robotics, with kinematics, with kinetics, as you're going to move forward, you're going to hear these terms more and more. Some of you may be familiar with this, some of you may have a background in engineering. For others, it might be the first time you're hearing these topics. So we'll take it slow. And if you have any doubts, please do stop me and ask questions. And in the second half, so we're going to take a break in between, maybe a 5 minutes, a bio break. And in the second half, I'm going to be talking about broadly, very, very broadly again, how we envision the role of AI in robotics, right? So this is going to give you a very, very bird's eye view. I know this is a very interesting topic. It's a topic that is very close to my heart as well. And I work very closely in this field. So you're going to spend a lot more time in upcoming lectures, but today is sort of the bird's eye view of where things stand, right? So 2024-25 has been a very interesting year for robotics in general, but AI in particular. If you've been following the news, all the Nobel Prizes, right? All, not without exception, all the Nobel Prizes this year, including those in physics, chemistry, biology, and in medicine, right? So all of this, not in biology, rather in medicine, have all gone to scientists and individuals who have made significant contributions using AI, right? We're going to look at one such figure today when we talk about our role of AI. He's a very interesting figure, right? So I'm not going to reveal his name. Very interesting, very controversial figure, was just awarded the Nobel Prize this year, right? So, and we're going to look at how he shaped our understanding of AI, modern AI that we know. Okay. So with that, we are at 12:41. So I will get started. So yeah, once again, welcome to the Executive Program in Robotics, Batch 2. So we are in session 2 of day 1. And this session, we are going to be talking about the present and the future of robotics, since you've already heard about the past. And we're going to start the first session with the classification of robots and then move into the role of AI, like I said. But before we do that, I would like to give you a more philosophical and perhaps a lighter look at what do we really mean by robots, right? So what is a robot? Now, how many of you know this gentleman over here, right? He's no longer alive, and his name is on the slide. How many of you know who he is? Many of you may have read his books. Yes, I think Matangi Venkataraman. Please go ahead.
So he's the guy who defined the laws of robotics.
And do you know his name?
Intention. It's written there. It's Isaac Asimov.
Yes. So Isaac Asimov, you're absolutely right. This is Isaac Asimov, very strange looking beard, right? And in some ways a visionary, right? So Isaac Asimov was a science fiction writer, prolific writer, right? And his views on robotics have, in some part, shaped how we think about modern robotics. And I Asimov never claimed to be a roboticist, never claimed to be anything other than a writer. But his thoughts and his philosophical take on robotics really has created a lot of new fodder for thought. And we're going to look at what his laws of robotics really, what his laws of robotics were defined to be, right? And remember that these laws were defined not to, not to build robots. It was defined to write novels, right? Interesting novels. And so these laws of robotics actually evolved as he wrote novels and as the need in his storyline changed. So these laws of robotics formally appeared in this beautiful book called I, Robot, which is also a movie in which we'll see a clip from that movie. by Will Smith. If you have not seen this movie, I would highly encourage you to watch this movie. And before you watch this movie, buy the book, right? And read it. This, I would say, if you ask me what is a recommended read for this course in robotics, I would say this should be your first read, right? So, how did Isaac Asimov back in the 60s envision modern robotics? Because at that time, there was not a whole lot of automation other than the assembly lines that were already present during the Industrial Revolution. What did he envision robotics to be, right? So he defined these broad laws of robotics, right? And the first law, and you'll see the importance of this law as we move forward. The first law of robotics, as defined by Isaac Asimov, was that a robot may not injure a human being, right? Please pay very, very close attention to the language that Asimov used and largely that we are going to be used to hearing, right? A robot may not injure a human being through its action, of course, or through inaction. So by not acting, it may not harm a human. So it's both its action and its inaction should not cause harm to a human being or allow a human being to come to harm. So if there's a possibility of harm to a human being, the first law states that the robot should act in some way in order to prevent that harm from coming to the human being, right? So this is the first law. Now, the second law states that a robot, as we all expect, it must obey the orders given to it by human beings. But there's a caveat to the second law, right? A very, very important caveat. The caveat is that it must obey orders only when it doesn't conflict with the first law, right? Which means that it will continue to obey orders until a human being is harmed, right? So it will not act in such a way that a human being will be harmed, right? So this places certain restrictions on the use cases of robots. Now, if you imagine, there are many, many robotic devices being used for military use. We know drones are a integral part of modern warfare, and they are autonomous, in some ways, semi-autonomous devices, and what would classify as a robot, right? By these two laws of robotics, perhaps, this robot would violate the second law and also the first law by extension, right? But then there comes a very important third law. The third law states that, a robot must also protect itself, its own existence, right? A robot has the right to protect itself. So it should be programmed not to cause itself any harm. And this is necessary because there are situations in which a robot is operating, and we'll see some examples of it. For example, in space, in a nuclear power reactor, where its protection becomes essential to its functioning, right? The function dictates that it survives that situation. However, again, the third law is subsumed by the first and second law, right? The third, a robot gets to protect itself only if it does not harm an individual, and only if it can obey the order of another human being, right? So if a human being orders it to be destroyed, self-destruct, the third law actually takes precedence, right? So these are the broad categories of laws that Isaac Asimov defined. But in a future novel, not in iRobot, Asimov then defines another law. And you would expect this to be the fourth law, right? Because the first three laws were already defined. You would expect this to be the fourth law, but it turns out that he had to define a zeroth law, right? A law that stands above in the order of, precedence. It stands above all of these first three laws. And notice how in the zeroth law, the definition of harm is broadened, right? Zeroth law states that a robot may not harm humanity, not human being, as in the first law, but humanity by action or inaction, just like in the first law, or allow humanity to come to harm. So there's a broader connotation, right? And this was, well, you could argue that Asimov always had this in mind and he just revealed it as a part of his plot. But it was beautifully portrayed that when you define laws narrowly in the context of the operator, in the context of just the human being, perhaps it's not enough in the broader context of things when robots may take up larger roles, right? And we are reaching that point where robots are no longer confined within factories, within industrial automation settings, where there is very minimal contact with the outside world. We're seeing more and more autonomous systems. We're going to define autonomy. We'll see what autonomous systems mean, levels of autonomy, and so on. More and more, these systems are coming in contact with what we would call more human beings or humanity in general. So now the concept of protection and harm must extend beyond the operator to humanity, right? There could be decisions, actions taken by a robot that could cause wider harm than just its operator, right? And notice that this is a zeroth law because this law must always be prioritized over these other laws. A very interesting exercise that I think every one of us should do is to try out different orders of these laws, right? So what happens if you bring the second law and place it before the first law, right? So you change the order of these laws and try and argue for yourself what situations can arise where the system can fail, right? And by and large, the goal should be to, of course, perform automation functions and in the long run, protect the robot and also uh, not injure the human being, right? So these three core tenets should be preserved, but you can try out different variations of this law and see for yourself whether other variations of this iterative laws rather could suffice, or is this the only possible sequence? Right? It's a very interesting philosophical thought experiment that you can do on your own. So now let's watch one short clip from the movie I, Robot. So just to give you some context, Will Smith is well, a law enforcement agent, and there is a large contingent of robots that are being built by a company. And this company claims that their robots follow all the three laws. In iRobot, the zeroth law didn't exist. So all the three laws, right? And Will Smith, the law enforcement officer, is skeptical. So we'll see how this plays out. I hope you were able to hear the video. So not audible. Okay. Yeah. Let me just try and see if I can even share audio. Share sound. Okay. Okay, let's try this once more. I hope that you'll be able to hear right now. If you don't, I'll share this clip with you so you can hear on your own time as well. Just let's figure this out. Yeah.
Unless the killer's still in here.
You're joking, right? This is ridiculous.
Yeah, I know. The 3 laws, your perfect circle of protection.
A robot cannot harm a human being. The first law of robotics.
Yeah, I know. I've seen your commercials. But doesn't the second law state that a robot has to obey any order given by a human being? What if it was given an order to kill?
Impossible. It would conflict with the first law.
Right, but the third law states that a robot can defend itself.
Yes, but only when that action does not conflict with the first or second laws.
You know what they say? Laws are made to be broken.
No, not these laws.
So in case you couldn't hear, Will Smith says that, these laws are meant to be broken, right? That's how it ends. So they were talking about these laws. And, if you look at the modern definition of robotics, right, you will see that these laws have all been rewritten, right? And rightly so, because this is a very philosophical take on how robots should behave. But if you look at a modern definition of an industrial robot, which is where primarily robots were meant to be confined. I mean, robots weren't meant to be in our homes, right? They've just made their way into our homes due to their immense capabilities. So if you look at the definition of an industrial robot, it talks about function, but not about safety. And that's how I think the modern definition of robotics has morphed. And this is something to keep in mind, right? So as a designer of robots, as a future prospective designer of robots, I think this modern definition needs some tweaking, but nevertheless, it is very, very important to understand how we define modern robotics, right? So an industrial robot defined by the ISO 8373-2012 standard, which is the standard for industrial robotics that's followed by ISO. It defines an industrial robot, and I'm going to read this word by word because it's very important. I generally don't like reading text of slides, but this is an important one. So please pay close attention. We're going to come back to this definition time and again, and I'm going to ask you what constitutes a robot, what doesn't, right? As per this definition. So an industrial robot is defined as one that is automatically controlled, very important, automatically controlled, reprogrammable, multi-purpose. Perhaps the word reprogrammable and multi-purpose are somewhat overlapping. Manipulator, right? So there is something that it manipulates, it changes. Manipulation means to change. That is programmable in 3 or more axes. Now you see that this is becoming much more technical, right? So this means that this manipulator is able to change something, most likely move in 1 or more axes, in 3 or more axes, right? Which can either be fixed or mobile. So the robot itself can be fixed to a platform, or it can be mobile, right? It could be a mobile platform that it's part of. And it's used for use in industrial automation applications, right? Now, there are 2 keywords that we need to discuss here. The first is, of course, reprogrammable. What does that mean? Of course, that means that the device has to be versatile enough so that its intended programmed functions can change without physical alteration, right? So the function is defined by the operator, right? Not by its physical shape dimension. That's how this standard seems to define it. Although I think this is a fairly old standard, as you can tell, right? It's almost 12 to 13 years old. And much of industrial robotics has changed since then. However, this reprogrammable term means that there has to be a level of versatility associated with the robots that makes it applicable to multiple industrial robotic settings without having to change the form of the robot, right? The function changes without change in form. So that is the important part of it. And then multi-purpose, which also has this very similar connotation, which means it's capable of being adapted or morphed different applications without physical alteration, right? The term axis defines directions, right? Which could be both linear or rotary. We are going to define what linear or prismatic joints mean and what rotary joints mean. So this motion spans all three axes, but could be linear or rotary, right? And we're going to look at two examples of the machines, right? And I'm going to ask you which of these two would you consider a robot as per this particular definition of a industrial robot. You'll notice both of these are in industrial settings. So based on that, which of these two would you define as an industrial robot? And of course, why? So in this first video, you see this worker sort of picking up what seems like a large wooden piece, most probably quite heavy, and requires some form of help to pick up. It would not be possible for one human being to pick this up, typically. And he's, well, manipulating the position and the orientation of these blocks, right? There's some assistance that is being provided by the robot itself, right? Or robot within quote unquotes, right? That you're going to define whether this is a robot or not. So this is instance one. This is a Dalmec industrial manipulator. So you can see that the word manipulator exists in its very, statement. So let's watch the second clip. This is a little bit more, right? So I'm going to mute this audio. There's no need for the audio. So this, as you might recognize, is a Tesla plant, right? Tesla is not going through such a great phase right now, but this is a video from last year. And I think Tesla has redefined the way we think of automation in car manufacturing, right? So as you look through this, you'll see that at multiple stages, we are able to see multiple different kinds of robotic systems, quote unquote robotic systems, doing several forms of manipulation with extremely hazardous conditions, right? I mean, typically a human being would not be able to perform these functions. So now the question is, which of these two would you consider a robot? Could be both, could be neither, could be one or the other, right? Which of these two would you consider a robot? And very importantly, why? Okay. So I don't know who has raised the hand. I think Joydeep Roy Chaudhary has raised his hand. Please go ahead. You would like to answer that?
Yeah, thank you very much for giving me the chance.
Sure.
Am I audible?
You are audible, yes.
The first one is not fully robotics, it's a collaborative robotics, as because it needs human intervention to function fully.
Right.
Okay, and second one is I suppose what I have seen in the clips, it's fully automotive situations and it's fully functional robot, which doesn't require any human intervention to operate.
Great. Fantastic. Thank you very much, Joydeep.
Thank
So,
you very much.
Thank you. So I think a lot of others also share the same sentiment. So I see that Jagdish, Avinav, Jayesh, Jayesh and Jagesh, both are all agreeing with you. So, and I fully agree with you, right? So just to reiterate what Jaideep said, the first robot, By the modern definition of robotics, this is what would be, as you rightly said, a cobot or a collaborative robot, right? A robot that primarily is assisting or augmenting human function. There's probably no automation involved in this because all the functions are manually being controlled by the human. But that is where the definition becomes a little fuzzy. I mean, in my view, you could have you could look at the intent of the user to change the state of the robot as an automation process itself, right? And we're going to discuss this later on when we talk about humanoids and other things, about wearable robots and assistive devices. But it's important to note that the function that the user is performing of perhaps, pressing on a joystick and changing the orientation, you have to ask, how is this different from picking up, let's say, brain signals from the brain and operating it, right? Are they fundamentally different? Would you call, if this was being controlled by a human wearing a EEG suit completely through their thoughts, would you still call this a robot? I think there's a fine line that we need to tread, but by this definition, you're absolutely right that this is probably would not be considered a true robotic manipulator, right? Whereas the robotic manipulators in the Tesla factory do not require any human intervention except for the first time when this was programmed. There is sensing and perception involved with these robotic arms. They will look at slight variations in the card positions, adjust itself, and then act accordingly. Whereas the first video, all of those functions, the sensing and perception functions, have been delegated to the human, right? You're depending on the human correctly positioning the robot. The robot does not have the intelligence to be able to do that by itself. And we are going to see that one of the three fundamental, there are three fundamental pillars of a robotic system: sensing, perception, movement, and control, right? So we are going to walk through all of these factors later on in the course. And the first robot lacks sensing perception, right? And the control aspect of it to a large extent. So perhaps even by that definition, even by stretching the definition, this would at most be called a manipulator. And that's what it's being called. It's not being called a robot at all, right? All right. So with that, let's look at some applications where modern robotics has landed itself, right? So modern robotics is extremely vast. I mean, it is impossible for us to probably cover everything in this course, and you'll see that the gamut of applications of robotics stretches all the way from space. And I'll show you two examples of how robots are being used in space. The easier one is the one at the bottom, right? So this is called the ERA, the European Robotic Arm. And as you might have guessed, this is in space. This is attached to the International Space Station, which, to my dismay, will be decommissioned very soon. But one of the greatest achievements of mankind, right? The International Space Station. So this robotic arm was developed by the European Space Agency and is attached to both sides of the International Space Station. So there are two such robotic arms. These are 7 degrees of freedom arms, and we're going to talk about what degrees of freedom mean in a future lecture. But they have, multiple manipulators and a robotic grasper at the end, right? So this helps in grasping different objects. In this case, this is a satellite that is actually grasping onto and perhaps launching, right? Interestingly, this system, once again, is operated from 3 different levels. I'm not sure whether this is visible, but this arm can be operated from inside the space station through controls, right? Can be operated from outside the space station using specialized base stations that are available, docking points that are available on the space station itself. And the astronaut can actually operate this from these control points. And then it can also be operated from the base station back at home on Earth, right? So it's an incredibly versatile device that helps in multiple functions, right? So and this is This has been there in a very harsh condition. As you know, space is a very, very harsh environment. There are multiple issues in operating electronic and mechanical devices in space. And the biggest issue is radiation, right? Solar radiation and other forms of radiation really affects these sort of systems. But the systems are designed to withstand such radiation pressures and the harmful effects of radiation, right? On the other hand, inside the ISS, you see this what is called a GEM ball. This was developed by the Japanese space agency. And this is meant to be a companion robot, kind of like a collaborative robot, right? Has multiple functions. It has both the function of providing some form of social and cognitive bond with the astronauts who spend several years. As you know, the ISS, several astronauts were stuck in space for a very long time, right? Due to multiple failures in launching retrieval vehicles. So these robots are designed to provide some form of comfort and social bonding. But more importantly, these are meant to almost be like a GoPro, right? Which is recording and monitoring and observing what the astronaut is doing and provide some form of safety in their operations as well. So when it detects something unusual happening, perhaps it can warn the astronaut that this is probably not something you should be doing, so on and so forth. So multiple functions. This is an experimental module that is there in space. And remember, this is in a very, very low gravity situation, right? So the dynamics of these sort of systems are very different on Earth than in space. And people have worked this out. And the next instance that we're going to show is in Fukushima. I don't know how many of you remember the Fukushima Daiichi nuclear power plant disaster. So there was a tsunami in Japan. I believe this was in the year 2008 or 6. I might be mistaken, so don't quote me on that. So there was this huge tsunami in Japan, and there was a nuclear power plant that was right next to the ocean. And this was a very well designed structure. However, seawater actually infiltrated into one of the reactors. And people had to shut off the reactor, and there was extensive damage. And the people could not access it. But to understand the level of damage and to assess what the future plan of action would be, the Japanese developed a robot, which was again radiation hardened and was operated from outside the nuclear power plant by operators who you can see are in masks already, right? And this was completely made to go inside the reactor and assess the damage caused. And there's a very nice article on this in the IEEE Spectrum magazine, which I would strongly recommend you to understand, right? So you can see that some of these functions are to augment and also to protect, right? So while we talk about safety and protection not being one of the focus of early industrial robotics, you can see that modern implementations seem to have taken that into account to some extent, right? And then we talked about the importance of robotics and social and cognitive. I mean, 15 years, 20 years back, you wouldn't imagine as a robot as a friend, right? But as you know, the Japanese society, once again, Japanese have been pioneers in modern robotics. So these systems have now been evolved to be social companions, right? And Japan is a society where the population is aging. There is a huge problem of loneliness and suicides in the Japanese society. So researchers, excuse me. So researchers are trying to find ways of adapting robots to be social companions. And this is one example of a device that was developed that has some of the social and cognitive skills of a child in order to provide companionship to young couples and, older adults as well, right? And then we have this another large sort of area that is ballooning, right? And has multiple applications, which is called collaborative or swarm robotics, right? So these are slightly different terms, but there are overlaps between them too. You've seen drone swarms, right? And this is both military applications, civilian applications. Um, IIT Delhi is home to a startup called BotLab Dynamics, which is doing fantastic work in this space, which is one of the which has held some of the largest drone shows in the world. I think it holds the Guinness record for the largest drone show in the world. And this is a completely homegrown company. So they build their own drones, they manufacture their own drones, they develop their own proprietary algorithms to connect these swarms and provide these light shows, right? And not just light shows, they're now moving into military applications where this could be used in surveillance, warfare, multiple different in rescue and search and rescue operations, right? So multiple different operations. But a thing that you see common is that the robots are meant to provide provide functions that a human otherwise would not be able to perform, right? That's the overarching goal of modern robotics. And the natural theme that you will see going around is that most of these robots are designed to move, right? So movement is a very crucial part of a robot, right? Although this was implicitly mentioned in the industrial robot definition through the term manipulation, which also means movement, right, of some form, a change in form. We see that most robots are designed to move, right? Again, starting from an industrial manipulator, right? We're going to look at these arms very, very frequently during the course of the of our learning. These are called KUKA robotic arms. There are many companies that make it, but this orange color is very distinctive to a company called KUKA, right? Again, a Japanese company that makes robotic arms, right? So this robot is fixed in its base, but movable, right? So there's a fixed and a mobile component to it. We probably all know what this is, right? This is the lunar lander that the Apollo missions, So again, wheeled systems. But would you call this a robot, right? I mean, this was operated, remember, by a human operator, completely by a human operator. So very little automation. So probably doesn't qualify as a robot. Whereas if you look at the missions to Mars that have been sent by NASA, right? The Curiosity, the Endeavour, all of these mobile robots that are now on the Mars surface and are pre-programmed to do a certain number of functions. For example, sampling of soil, looking at the Martian environment, uh, looking at the Martian, atmosphere, sampling, doing scientific experiments. All of these are actually automated, right? So the commands are sent, but the monitoring of this device is happening internally. So there's sensors and transducers that are doing this act of drilling and then figuring out whether it has drilled to the right depth, uh, doing the scientific experimentation of, let's say, understanding the moisture level in the soil. So all of this is automated to some extent, right? So the modern version of these rovers that are being sent to different planets, including our own very own Chandrayaan, right? They are completely autonomous, right? So we are trying to make them as autonomous as possible. And we're going to look at what levels of autonomy mean again in the next lecture. And then you have autonomous underwater robots, and not just on the surface, but underneath the surface. Again, these are controlled through a human operator outside, right? So on the surface, usually there's a surface ship and there's a tether, right? So there's a tether which allows signals and commands to be sent, and this is controlled in real time using. So this is a underwater autonomous robot. And now you'll see that there's also an interest in developing underwater robots, which have humanoid form, right? And there's this concept of why we want humanoid forms, or rather anthropometric forms that resemble uh, um, resemble the human form, right? So, by the way, this professor that you just saw, Osama Khatib, is extremely famous. I mean, he's considered one of the pioneers of robotics. So Osama Khatib has a handbook of robotics, which is probably 6,000 pages. He's famous for that. So his lab has developed these devices which allow very, very close manipulation of uh, underwater objects. It allows the user to see in real time. And of course, when you have these humanoid and anthropometric forms, it's very easy for a human operator to actually imagine itself and then grasp onto objects. And we're going to see one example of this sort of manipulation when we talk about surgical robots. And just note this image here where you're seeing these robotic manipulators being used to gather the information from the user and then translate that into movements of the robot, right? So remember these images and you will see the similarities between these systems and modern surgical robotic systems. And then, of course, you have aerial robots, right? I mean, we're all very, very familiar with the modern drone systems, the modern systems that really look at uh, swarms and so on and so forth, right? Move on to the next slide. And uh, what we are seeing is, these forms of robots, underwater, overground, mobile, robots that are aerial, have flight capabilities. All of these functions are now also morphing and becoming multimodal. So a single robot can have the capabilities of both a wheeled mobile robot as well as a robot that has capabilities of flight, right? So this is an example of work that is being done at Caltech. Let's see if I can. Oh, yeah. Yeah. Work that is being done at Caltech. You'll see that in this normal configuration is this robot is simply like any other wheel robot, perhaps not a very capable wheel robot, but nevertheless it's able to go over simple terrain and so on. And soon you will see that it morphs, right? It changes its function and form to an aerial robot, and you can understand how versatile this is and how useful this could be in situations where, like this, right, where there's an obstacle that a wheel robot would not be able to perform. So these boundaries of classifying robots, my whole aim of showing all this is that we're going to be talking about classification of robots, but these boundaries are very blurred now. People are changing these boundaries. Researchers are changing these boundaries every day. Okay, it's very important to know that while we look at these definitions, it's also very important to understand that you need to break out of these boundaries of definitions and classifications. It is our job to show you this, but it is also a job to question and look at different forms of these robots. All right, so more about these robots in this link. So please go and read these references. If some of you were asking for additional reading material, I think some of these reading material will be on the slides itself. So please do, and please refer to these materials, right, as and when they are made available to you. So now that we've seen that robots come in all forms of shape, sizes, morphable, non-morphable, right, single function, dual function, so on and so forth, can we bring some order and some some sanity to all of this, right, in some sense? So can we start with some form of a classification system that hinges on the power source of the drive technology, right? So every robot will require some form of electrical to mechanical conversion of energy, right? And this conversion technology can often drive or can be used to classify the kind of robot that is being that we're talking about, right? So just simply based on the power source or the drive technology, you can think that this can be driven typically by electric motors. I mean, that would be the first choice, right? Because they're cheap, they're versatile, and again, within electrical motors, you have two kinds of motors, so DC and AC, right? So on the left-hand side, or all of these pictures that you see over here are all DC motors, different kinds of DC motors, and we're going to come to the different kinds of DC motors later on. But broadly, these could be stepper motors, which move in discrete steps, to geared DC motors, which have very, very high torque capabilities, to brushless DC motors, which have very high RPMs, right? So they're typically used in drones. I've shown one use case of each of these motors. So for stepper motors, these are extensively used in Cartesian and other forms of 3D printers, right? Which are also a form of automation and robotic systems. So this is a Prusa robot. You're going to yourself make wheeled robots. So many of these wheeled robots will come with normal geared or ungeared DC motors, right? These DC motors are used for multiple purposes to drive flywheels, for example, and so on, right? And then you have these brushless DC motors, which have become extremely popular for its lightweight and high RPM production capabilities, and very, very commonly used in drones. Like all the rotors in a drones will probably be a BLDC or a brushless DC motor, right? Again, DC motors, you will see extensive use of them in mobile robots, right? And the reason why they're used in the mobile robots should be obvious to you, because DC motors can be powered through batteries, right? It's fairly easy to provide power to a DC motor using a battery powered system, which is what a mobile robot would want, right? A mobile robot would want to be mobile, which means it has to be powered through your DC power sources, which are batteries. On the other hand, we have AC motors, again, extremely useful, but usually much larger in size and used in typical high power applications, typical industrial robots, right? So if you see an industrial manipulator, the joints, these joints that you see are all AC motors. They're not DC motors. They're all AC motors, and they operate through alternating current, not DC. And because they operate through AC motors, and typically AC motors are also large in size, they will typically be tethered, right? Which means that it is very hard to carry them around. So mobile robots, by and large, right, unless there's a exception, by and large, you'll see that AC motors are used in fixed type of robotic systems. But again, they produce much, much higher power than DC motors, right? Of comparable size. So that's the important part to note. Now, with AC motors, just to add to this, that in general, it's very hard to convert DC to AC, right? Even electronically, it is not easy to convert battery power into an AC power. So that is also one of the reasons why you don't see AC systems on a mobile robotic system, right? Even though if you can place an AC motor, which is large and heavy, the act of generating an AC alternating source from a DC source would itself be quite difficult and power consuming, and it's a lossy system. Hence, typically people don't use this, right? So this is one way of looking at at robots, robotic systems, and how you would classify it based purely on the electrical motor drive technology. Now, apart from electrical drives, there's a vast category of robots that do not use electrical drive systems at all. And modern robotic systems are, and very high-powered systems. You'll see that a lot of these systems will typically use hydraulic or pneumatic robots, pneumatically powered actuators, right? And with hydraulic systems, as you might know, these are powered by liquids, right? Hydraulic means it's some form of liquid. So hydraulic liquid is used, so fluid is used. They produce extremely high torque, right? Extremely high force production capabilities. But of course, because this is a system that is based on a fluid, it is also very difficult to maintain, right? But they're extremely robust at the same time, right? So they're used in very harsh environments. For example, in this, you all know what this is. This is a JCB. There's a manipulator arm, right? Which is, of course, not a robotic arm because it's being controlled by a human operator. But all of these joints, right, are being controlled by hydraulic systems, right? So when these hydraulic systems extend, so there's a linear hydraulic actuator, it extends, it converts that linear motion into a rotary motion, right? Very high, very, very high force, and you know the power of a JCB. And at the same time, very hard to maintain and very noisy. And one example of how noisy it can get is this robot from Boston Dynamics, right? So this, I hope most of you have heard of this company called Boston Dynamics. They produce some of the most innovative work in robotics and humanoid robotics in the years. So this is a precursor of their early system called Bison, this one is called Wildcat. So the Wildcat system is a completely hydraulic based system, and you'll see this is an untethered system, and you'll see how loud it is. Okay. Right. So I don't want to torture you with this noise any longer than I have to. But one of the reasons why this is, oh wow. Okay, I think that's enough of Wildcat, right? So one of the reasons why this is extremely loud is because most hydraulic systems require a compressor, right? Some form of a fluid pump and a compressor. So this hydraulic system is being powered by there's a there's an engine which is attached, which is producing the kind of electrical power required to drive these systems, right? So that is why it is extremely loud. And even a JCB can be quite loud, right? So this is because this requires pumping pressures that are extremely high. There are pumps that are required to be operated, which makes it extremely difficult to operate. On the other hand, you have pneumatic systems, right? So you have pneumatic systems, which are operated not through a fluid, not through a liquid, but through air, right? So pneumatic systems operate through some form of gaseous medium, primarily air, could also be other low heat expansion, thermal expansion gases like nitrogen and so on, but primarily using air. And so these pneumatic systems have been extensively used for multiple applications. Pneumatics is something that is very commonly used in robotics, mostly at the end effector level. So you will see that pneumatics are being used to develop a lot of graspers. So when I go and pick up something using a robot, the end effector, the device that is actually providing the action of grasping, now a lot of these systems are pneumatic, right? Because you can have a very soft, deformable robot that can be used. So a lot of this focus has shifted to the end effector, but early work in pneumatic systems, you'll see, looks at development of systems that emulate human muscle. So this is from a company called Festo. Festo is a very famous robotics company which makes several different kinds of robotic automation systems. And this is a particular system which they developed. This is called a Festo pneumatic muscle. And as you can see from this video, there are air supply lines that are going into this thing. And as this pneumatic line actually expands, it also contracts in its length, right? So you'll see that the cross section of this pneumatic actuator is increasing, and as a result, it's shrinking in size, right? It's designed to be that. So as soon as you increase the air pressure, there's lateral strain, which increases the size, and there's a tensile load that can be picked up, right, as a result. So this is an example of a pneumatic system. Similarly, this is also another example of what is called a pneumatic artificial muscle, or PAMS. So this is from a lab in Harvard, the Harvard Biodesign Lab. So they have been designing these soft robotic systems. We're going to look at these systems extensively later on. You'll see that these orange colored actuators are providing assistance to a human subject during walking, right? So this can reduce the effort of walking for an individual. And this could be used in rehabilitation where individuals have different forms of gait. But as this video slows down, you'll see that as the ankle pushes off, right? So you'll see this is a push-off stage. You'll see that these actuators actually expand, which makes them contract and provide a little bit of tugging force on the ankle, right? Which provides a little bit more force during the ankle push-off phase. Just to play this once again, right? When you see this toe-off phase, right? When the toe actually hits and lifts off, which is when you have this propulsion, you will see that there's a little bit of expansion on on these muscles, which is providing a tugging force on the ankle itself, ankle joint, right? Which helps with that propulsive force. So it reduces your effort. So the effort that you put in during the walking is being supplemented by that joint, right? So this is all examples of pneumatic and hydraulic systems. Typically, pneumatic systems are very high speed and usually very easy to manufacture, extensively used in rapid manufacturing lines. But the issue with pneumatic systems is that they're also very low precision, which means that their repeatability. So if I provide a certain amount of power or certain amount of pressure and inflate a particular of these pneumatic actuators, my ability to recreate the positional change would not be very precise, right? It would have sort of varying levels of precision. Okay? And that is why you will see a lot of these pneumatic systems sort of not being used commercially for large level actuations, because they can have large tolerances, large errors associated with them, right? But they're used as end effectors in rapid manufacturing lines. We'll see examples of it later on. Okay, so now we come to a very important part of our discussions, which is how to classify robots. And I think this is a very, very important part. How to classify robots based on their workspace geometry, right? So every robot has a sphere of influence. When I say sphere, I don't necessarily mean an actual sphere. I mean, there's a area that it can manipulate within, right? And this space is called the workspace of the robot, right? And different forms of robot will have different kinds of workspaces, large, small, different volumes, different shapes they enclose, right? And based on the kind of workspace geometry they enclose, you can classify different robots. Okay? The most simple form of workspace geometry is provided by what are called Cartesian robots, right? So Cartesian robots, as the name suggests, follow a Cartesian coordinate system, right? The name comes from the Cartesian coordinate system, which is X, Y, and Z, right? So X, Y, and Z. And this definition of what is X, what is Y, what is Z generally changes, right? With different manufacturers and so on. But the three axes are translational axes, right? And usually these Cartesian joints or Cartesian robots are made up of prismatic joints. What are prismatic joints? Prismatic joints are essentially joints that have translational motion, movement in one axis, linear movement in one axis. And when you combine three of these prismatic joints, so in this case, if I look at this diagram, so let me switch over to the laser. Yeah. So when I look at this diagram, there are three prismatic joints, right? The first prismatic joint is around the x-axis, right? So there's a linear translation along the x-axis. There's a linear translation along the y-axis, and there's a linear translation along the z-axis. We're going to ignore the ability to rotate the z-axis of the end effector, right? So this end effector may be able to rotate, right? Now, if you imagine that I'm able to move this robot along x, y, and z, the workspace that it will enclose will be a cuboid, right? So it will be a cuboidal shape that it will be able to uh, manipulate within. So any point within this space or within this workspace will be accessible to this robot, and it can manipulate within that geometry. Okay. So very importantly, Cartesian robots have prismatic joints, typically three prismatic joints, and it's called a PPP configuration. So three prismatic joints, PPP, right? Very easy to understand, usually very fast movements, simple geometry, very easy to build, and also easy to compute. Everybody understands X, Y, and Z, right? So you mention one coordinate, let's say 3, 3, 5. You know exactly how much the x-axis has to move, the y-axis has to move, and z-axis has to move. This provides for very easy translation of these coordinates or movement into kinematics or actual movement of the robotic system, right? Very, very common in industrial systems, in many different systems, and are widely used in pick and place operations. So where you have to pick an object and place it, used extensively in CNC machines, right? Where you see robotic carving and so on, and in gantry stages, right? In any form of gantry system, like let's say, as you will see here, you will see a robotic pick and place system. Right? So this system has three prismatic joints, right? So essentially, there's one linear translation happening along the x. There's one happening along the y, which is on this head, right? And then on the z-axis, right, you have up and down motion, right? So you can see that it's moving up and down in order to pick up objects, right? And you will see similar systems in industry all over. So you'll see nowadays people are developing these, 3D printers for the construction industry. So a lot of these are used, very extensively used in the manufacturing industry for movement of objects, right? Very simple to use, very robust, very fail-safe in some sense, right? If you want to know more about these geometries and how they're defined, I'll refer you to this International Federation of Robotics document, right? Which talks about the different geometries and how they're defined in an industrial setting, right? So please, this is an additional reading material that you can refer to, right? So with this, we are about at the 1 hour mark. So I'm going to take a brief bio break for 5 minutes. It's 1:43 now. So let us reconvene. It's 1:44 as I speak. So we'll reconvene at 1:49. Okay, 5-minute break. Okay. Thank you so much, and we'll continue the lecture from there on. Thank you. Yeah, so somebody has asked, please mention the magazine, the link, if available, for the Fukushima story. Yeah, so all of these are available. I've shared the links. The slides will be made available to you. So please access those links directly from the slide. But the name of the magazine was IEEE Spectrum. Okay, so IEEE is the premier body for in electrical and electronics engineers. So they produce a magazine called IEEE Spectrum, fantastic magazine. So yeah, all right. So we'll reconvene at 12:49, 1:49, please. Okay. So we'll restart again. So so based on workplace geometry, the first kind of robot that we saw was the Cartesian robot, which has a PPP configuration or a prismatic configuration. Right, so 3-axis, 3 prismatic joints. The other kind of joint that you can have is a revolute joint, right? A joint that revolves around its central axis, right? So very simple to look at, and that gives us additional options in defining workspace geometry. So let's look at some of these options, right? So one of these configurations that we can come out with is by replacing one of these joints in a Cartesian robot with a revolute joint, right? And in doing so, I end up with what is called a cylindrical robot, right? You can imagine that if I change the x-axis of the Cartesian robot to a revolute joint instead of a prismatic joint, now we have a revolute joint. I end up with a cylindrical workspace, right? Why? Because I can rotate this joint, and hence I get a round shape here, and I can move up and down, and I can move back and forth in the z-axis. As a result, I get a cylindrical volume in which I can manipulate objects. Now, these robots are not as common, right? These were used in slightly older systems, in systems where different kinds of tools are used. They're used in CNC machine tool loaders. They're sometimes used in the hotel industry and so on. But the advantage of these systems is that, of course, very simple geometry. Again, you can define any position using 3 coordinates, right? So Z, Y, and the theta, right? And it's very easy to compute. However, these are typically slower than other configurations. The reason is the inertia caused by the revolution, right? Typically, there'll be a much slower system compared to a Cartesian equivalent of it. Now, I want to show you one video. It's not easy to find cylindrical robot videos, but I want to show you a counter example, actually, right? So I want to show you an example of what is a CNC rotary axis. The CNC machine essentially carves different kinds of objects, and typically, we search for a CNC system, they'll all be Cartesian robots, right? However, in a CNC machine, you can add a rotary axis. So let me just orient you with this video first, and then we can come back. Yeah. So as you can see that there is a Cartesian system of prismatic joint, and you will see the prismatic joint onto the other side as well, right? So X, Y, and Z are a Cartesian system, and you'll see this tool head going up and down. Okay, but in addition to the still head going up and down, you're also going to see that there's a rotary axis, there's a revolute axis, right? This is moving. Now, look at what is going on. So there's a piece of wood which is being carved. The z-axis is moving up and down, and there's a revolute axis. So this is even clearer, right? Where you see that there's a revolute axis. Now the question is this an example of a cylindrical robot? Right? There's no right or wrong answer. This is something that you need to think about at home and let me know maybe in the next class, right? The question is this an example of a cylindrical robot or is it not? So you have to be able to justify whether this is an RPP system or not. Okay. All right. So moving on. Yeah. So another form of robot where we replace not one, but now 2 of the joints. As you will see that we're now moving towards a system where we have replaced not 1, but 2 joints as spherical, rather revolute joints, right? So earlier we had replaced the x-axis as a revolute joint. Now we are also replacing the y-axis as a revolute joint, right? So now this arm rotates about this axis and rotates about this axis. One is called theta, the other is called phi. So two revolute joints. And additionally, you have a z-axis prismatic joint, right? So it can move back and forth with this prismatic joint. Interestingly, this was one of the first implementations of an industrial robot, a robot by the name of Kawasaki Unimate, right? You don't find these robots anymore, but highly successful device used in several automation systems across the world. Highly successful device. However, this is a very big flaw. The flaw is the ability to not be able to translate along this axis, right, which we were calling y-axis. So there's no way to directly move in the x-axis. So every movement in the y-axis, sorry, in the up and down direction has to be through a circular motion, right? So which makes this device somewhat unusable. And if you look at the volume, it's a spherical volume. That's why it's called a spherical workplace geometry, right? And there will be a large dead space around the base of it, even though it shows like the sphere being able to reach here. If you look at the video, I'll play the video of the Kawasaki Unimate. Okay, this is the Kawasaki Unimate. If you notice that the design of this robot, right, doesn't allow it to access several different points. So there's going to be large dead spots near the base, right? Near this spot, it will not be able to access simply because of the geometry of this system. It was used in the automotive industry, extensively used by Toyota, very, very extensively in Japan, right? And at a certain point in time, it was extremely popular. But then people realized that you don't really need this prismatic joint. You can change all three to a revolute joint and get what is the modern version of this articulation arm. And this is called an articulating arm. And you will see this in most automation systems in automotive and many, many robotic automation systems, right? And in this case, we've now replaced all three axes with revolute joints, okay? Theta, phi, and psi, right? Three joints, okay? So one at the base, one over here, which changes this, and then this joint, which changes the phi, right? Three joints. And this is a very, very versatile device. And because this operates only with revolute joints, which means it can be operated using using motors, it is extremely easy to manufacture. So as you can see, this is a FANUC robot. FANUC is a company that makes these robotic articulators. The different motors are placed directly at these joints, right? We'll see how belt drive is used to manipulate these joints, but we'll see that this is very, very easy to manufacture, right? You just simply place motors at these joints and you're done. Right? And because of their versatility, they're used extensively throughout the industry. There are several manufacturers. Among the industrial manufacturers, the biggest names are FANUC and KUKA. All right. Okay, good. So as you can see, most robotics systems nowadays will operate with these sort of systems. Let me see if I can change the quality. Yeah, but you must have seen videos of these systems at work, right? So that these revolute joints are extremely versatile. We'll talk about the workspace of this when we come specifically to the articulating joints. It will be a little difficult to talk about the workspace of an articulating robot now. Okay? But the workspace is not as simple as it looks. Okay? So it has a slightly more complex workspace. But the systems are used to the computations are not that difficult. Okay. Okay. So now we have talked about classifying different robots based on their workspace geometry. Now there's another way of classifying robots, which is based on their kinematic structure. Right? Kinematics is the way that the robot moves, right? The study of the position, velocity of the robot. So kinematics applies geometry to the study of movement, right? And based on kinematics, we have a couple of different kinds of robots that you can build. One is called a serial kinematic structure or a serial robot, right? So if you look at all of these structures, what you will see is all the joints are serially connected with each other, end to end, right? So they have an open loop structure, which means that I start with one joint, I connect when the joint ends at, when that arm ends, I have a joint, I connect another actuator at this joint. When that arm ends, I connect another actuator at that joint. Right? So if I look at the previous video, there's one motor here, serial, then one motor here, another serially, right? So they're connected back to back, correct? And all of these configurations that we defined, or at least in this case, what we define, are all examples of serial. You can see that they're all connected back to back, one after the other. Okay. So serial robot is one where the joints on the rigid links are connected back to back. Right? So rigid links are connected to the joints serially. Okay. Can anybody tell me what is the disadvantage of a serial robot? Yes, Agnishekhar, please go ahead.
I believe the degrees of freedom will be limited in this case. The area
Yep.
of the reach in generally, which is important for any robotic application, will be limited, and also we will probably will be having a pleasant number of provisions for end effectors to grip the materials where it is being picked and where it is being placed. So, to my knowledge,
Okay.
that would be the case.
Okay. So you're saying that there will be two disadvantages. One is the reach of this device, and the second is the options available for end effectors. Okay. All right. Any other points that anybody would like
One
to
more
share?
thing will be the degrees of freedom.
Okay. Why do you say the degrees of freedom will be a challenge?
See, because
Can we
if in
not build
case,
a?
sorry,
Yeah. Please go ahead.
no, I say this because in the regular application which we see in the industries, there are different areas where there are different materials which has to be picked and placed. So it cannot be only linear kind of a motion. Either it's vertical or horizontal. It cannot be. It has to be some other areas also which has to be covered. So probably the area
No,
of
but
access
so just to correct you, we're not
is please.
talking about linear actuators only, right? I mean, you could have all three revolute joints. So for example, this is also a serial robot. There are no
Yes.
linear actuators, right? I mean, you could, all of these are revolute joints, right? So all of these are revolving. And so in theory, right, these are all revolute joints. So, and this is a serial robot, and there is a workspace that it can talk about. So I take your points. So and so let's discuss a little bit more. So I see a few more hands. So in order, so I think Harsh Mohanty and then Shanmugam, and please. So Harsh, you can unmute him. Yeah.
So I think because of the because of so many joints, I think failure of one particular joint may result in, progressive and chained failures, is what I think.
Excellent, excellent. Yeah, that is a very, very good point. That since these joints are connected in series, failure of one joint could lead to the failure of the entire mechanism, right? So they are not fault tolerant in some sense. That's very good. Very good point. Thank you. Okay. Any other point?
Thank you.
Sir, this is Shanmugam here.
Shanmugam, you are not audible. Yeah, please go ahead.
Am I audible right now, sir?
Yes, your voice is breaking up a bit, but please go ahead.
Sir, I think the problem with the serial manufacturers are it requires more torque motors, right? Because the end effector need more torque need to be actuated. That is the main
Yes.
problem with the serial motors, sir.
Fantastic. Thank you so much. So Shanmugam and Harsh mentioned two very important points, right? So first thing that Shanmugam mentioned was that imagine being the base motor, right? So this base motor will have to be an extremely strong motor because it is carrying the weight of not just the rigid links, which are typically made of steel, right? And they're also carrying the weight of the rest of the actuators. All of these are serially connected. Of course, you can argue that these actuators could be placed at the base and belt driven and so on and so forth. But typically, they're all placed close to the actuators, close to the joints, which means that progressively you're going to have extremely high torque. You will need very high torque actuators to be able to design these systems, right? So one of the main disadvantages of having a system is that one, the actuator weight has to be carried by the entire base assembly, right? And because of this, you will need to make motors. So at the end effector, I think this is something that the first participant mentioned, that at the end effector, you will have very, very little choice, right? So you'll have to have very light end effectors. So graspers, grippers have to be very light because otherwise the entire weight of this grasper is falling on the actuators that are at the different joints. So therefore, the effective payload that can be carried by these has to be very light. They're not designed for heavy payloads. Also, another big disadvantage is that imagine if I have progressive errors. So let's say if I ask this joint to move to 10 degrees and it moves to 10.5 degrees. Every joint moves to a slightly different position, let's say by 0.5 degrees. These errors will start accumulating, right? Because these are serial, the 0.5 along with the 0.5 of another, along with the 0.5 of the next joint. Because these are serially connected, they will all add up to have large errors in the end effector position, right? That is one big issue. And the last issue is, you can probably also guess, that these systems are very low stiffness. Look at all of these systems, right? If you look at it, they all have end effectors which have very large amount of translation, right? Or they're jutting out, so to say, if you want to have a layman's version. So all of these systems, because they are sort of serially linked, they will not be very rigid, right? It will be very easy to sort of push and nudge them and have a lot of vibrations and low stiffness, right? You can imagine having a very long arm. At the end of that arm, if you put a lot of pressure or weight, the system will not be able to sustain this, which is also the reason why it has a relatively low effective payload. Okay. But at the same time, I think somebody mentioned that it has a limited workspace. Actually, on the contrary, it has very large workspace. Why? Because these are serially connected. So you have a very large reach, right? So you connect rigid link joint, rigid link joint, rigid link joint, rigid link joint. And technically you can keep connecting as long as your your actuators support it, right? So you have generally a very large workspace. which is an advantage, space loading, low payload, errors are accumulated, and this has a low stiffness, right? Hence, you're going to get somewhat imprecise movements. Okay? On the contrary, to serial structures, you have what are called closed loop or parallel structures, right? But before we move to serial structures, can anybody tell me what is a biological structure that has a biological system, right, which has a serial structure?
Hands?
Can you, would you say hands or would you say arm? So there's a difference between hands and arm, right? Hand is this, arm is this.
Arms and legs.
Sorry, I tricked you. It's both hands and arms, right?
Okay.
Hands are also, yeah, you're right. Hands was right. I'm sorry. Hand is also right because this is a serial structure. So if I look at my fingers, there are 3 joints in my fingers: interphalangeal joint, metacarpophalangeal joint, right? So there are 3 joints. Then you have your wrist joint, and the thumb actually has the 3 degrees of freedom, right? So you have this translation, you have this thumb adduction, abduction. So very complex, but these are all serially connected, right? One after the other. And so is the arm, the elbow joint, the shoulder joint, the wrist joint are all serially connected. Okay, so this is a biological structure, and of course, you know why the hands are built serially, because you need to reach out for objects, right? But at the same time, you will see how when we reach out in the front, we don't have the kind of precision that we need, right? So when I'm stretching out my hand and manipulating, I will not be able to write like this, right? When I stretch my hands and write, it will not be a very nice handwriting. Why? Because I have low stiffness, my errors are accumulating, right? And hence my precision at that tip is reduced. And of course, because of my outstretched arm, I won't be able to hold like a 10-kilo weight, right? If you give me a 10-kilo dumbbell, I will not be able to hold it. So you will see how our body adapts to this, right? So let's look at parallel structures. So in parallel structures, I'm sure you've seen this sort of a platform before. This is called a Stewart platform. This is the most common form of parallel structure. So the easiest way to understand parallel structure is that it has several actuators or several serial chains which are connected to the same end effector. So in this case, the end effector is this platform. You can see there are multiple manipulators, right? Multiple actuators. And these could be many, many serial links also, 3 or 4 links. In this case, there are only 2 joints, right? There's one joint over here, and then there's one joint over here. These are both universal joints. And these joints connect the this platform. But they're all acting in parallel, right? So if I look at it, they're connected to the same base, they're connected to the same end effector. So one joint, right? So the end effector and the base has multiple actuators and serial links that are connecting them. So the question is, why would I want to do this? Right? What is the point? It seems redundant. Of course, this provides us the ability to do multiple different things. So we look at some of the advantage. First of all, the big advantage is that now if you look at it, now because I have all these parallel arms, right, the system has become extremely rigid. You can physically understand that the system will be able to carry a lot of load, high workload, load capabilities. It will be able to generate extremely high power because it has multiple actuators working on a single platform. And it will be extremely rigid, right? So when I try to move this, it will not be able to move because there are multiple systems and multiple constraints that are present, right? As a result, it will be extremely high precision and lower. So these sort of systems are used where very high precision is required, parallel robotic systems. So if you're manipulating something and you want extremely low error, because these errors don't add up, right? Like in a serial link. But the big disadvantage is they will tend to have a very small workspace because they're all acting in parallel. That reach is not there. Okay. Commonly, these are used in simulators. You will see, like, I don't know whether you've been to like a science museum of some sort, where you will see these sort of simulators. These are used for aircraft simulation. Steward platforms are very commonly used. So this is an example of a parallel closed loop structure. Closed loop structures, like I said, tend to have smaller workspace, but newer parallel robotic structures are trying to defy this. I'll show you what I mean. So this is a very nice example of a parallel robot, right? And this is cable driven. So you will see this looks kind of scary. Let me first orient you to this video. Sorry. Okay, so stop it at the right time. Okay. So what this is well, there's a platform on which a user is sitting, and then there are cables which are connected to different points on this huge room. Right, they have a lot of space, so they've connected different joints through universal joints to this to these actuators at the different corners of the room, right? And you will see how this, when these cables are drawn, you can imagine when I tug on this cable, right, the system will want to rotate, right? When I tug on this cable and this cable, it will want to rotate. Whereas if I tug on all of these cables together, I can move it to one side. So you can have both translational and rotational degrees of freedom. Okay. So let's see how this works. It looks extremely scary, right? So you can see that this system is being lifted simply by changing the lengths of these manipulators, right? Of these cables, right? So these are winches that are drawing on these cables. And you'll see how fast this system can operate very, very precisely because it's constrained on multiple ends through this cable-driven system. So very rigid, very high precision, repeatable, and at the same time, it has a very large workspace, right? So this is being used to train pilots in, say, helicopter simulation and so on. Okay, so this is the advantage of a parallel closed structure. Now, in the previous slide, we looked at serial structures and we said that our arm is a serial structure. And we saw the disadvantages of a serial structure, right? Which is that it has low precision, which gets much of it gets solved in a parallel structure. Now, see how beautifully our body adapts to this serial structure, right? So here are two of the greatest players in tennis, right? You will probably all recognize them. On the left is Roger Federer, and on the right is Rafael Nadal, right? Two of the greatest rivalries in one of the greatest rivalries in modern sports. So Nadal was known for his powerful shots. So he was known to have very powerful shots, while Federer was known to have a very powerful backhand, right? A very precise and powerful backhand, very fast ability to respond to these shots through backhand. Right? But if you look at them, they fundamentally use a different strategy. Right? So look at what Rafael is trying to do, right? Nadal is essentially holding onto the bat using two of his arms. And therefore, if you look at it, this is the end effector, the racket is the end effector. And the two arms are two serial links, but connected to the same end effector. So therefore, Rafael is using the advantage of parallel closed loop structures to generate more power and have perhaps more precision, right? While doing so. And perhaps the secret to his power in his shots is the use of a parallel structure, right? Whereas if you look at Federer, and you can look at multiple videos, this is not just one clip. But if you look at Federer, he uses a single hand, which is a single serial structure. We know the disadvantages of it. The disadvantage is that he will not be able to generate as much power, and rightly so. Federer was not known for his power. What he was known for was his ability to reach at impossible lengths and drive these backhands. So this serial structure gave him a different kind of advantage, but both have their use cases. So the body, you have the ability to adapt to the situations and have serial or parallel structures, right? The same structures can be adapted to have a parallel structure. Okay, and you can see the advantages and disadvantages. Even if you don't have these manipulators at home, you will be able to tell the difference between these systems just by using parts of your body. And I would highly encourage you to try out different experiments in this fashion. All right. So now we look at two special robotic configurations. Okay, one is called a SCARA robot, right? This is a fairly commonly used robotic platform, and the other is called a Delta robot, right? So what you will see is in a SCARA robot, there are two joints which are revolute. One is this joint, right? So this is a revolving joint. The other is this joint, which is also a revolving joint. So these are both independently controlled. And then there is the prismatic joint, which is at the end effector. So it can pick up objects like this, right? So let me play this video. Show why this is giving me trouble today. There you go. So if you look at it, you can see that the end effector is moving up and down, which is picking and placing objects extremely precisely, right? And the reason why you have this precision is because you have two manipulator serial arms, right, which are able to operate in parallel, right? So this is an example of a parallel robot, right? There are serial versions of SCARA robots as well, but this is a parallel version of a SCARA robot. Okay? So if you Google or go on Wikipedia, you'll perhaps see a serial version of a SCARA. This, on the other hand, is a parallel version because there are two end effectors, two actuators, which are manipulating a single end effector through two rigid links, right, connected to the same arm. So this is an example of a parallel robot. Okay. The advantage of a SCARA configuration is it's extremely high speed, right? Very, very high precision, which is a common functionality in all parallel robots, and high payload, right? So it's able to pick up very, very high payloads because it's being controlled through a parallel configuration. On the other hand, we have what is called a Delta robot. These are used in pick and place applications. Pick and place. So in pick and place applications, you'll see that this is a FANUC robot, which is used for pick and place. You'll see that these robots have three manipulators, all revolute. Okay, RRR, three revolute joints, one over here, and the other on the other side, which you can't see. And they're connecting these arms, serial arms, to a single end effector. So we'll see this video first. Very fast, very precise, used for robotic pick and place. But in this configuration, they have a very light payload capability. They're not able to support a large payload, but extremely high precision and speed. So used in light pick and place applications where precision and speed is the priority, right? So these are, you have to decide which of these are serial or parallel robots. So please answer these questions at home for yourself. I'm going to share the slides. You'll see which of these. So the question is, the SCADA robot is a parallel robot. It's clearly written that it's a parallel robot. What is a Delta robot? Is it a serial or a parallel robot? And why so? Answer is fairly simple. Okay. So with that, I'm going to move on to the next set of questions. So I think Joydeep mentioned 219, so I'm guessing it was a while back, that he begs to differ. So I'm not sure which part you differed with, but we can come back to it at the end of the of today's session, right? Which is going to be soon. Okay. Okay. So now let's try and understand. We want to, churn up our memories and sort of look at some of these examples and try and answer these two questions for ourselves. Okay. So this is an open question to everyone. So I'm going to show you a video. This is a video from YouTube, and I would like you to look at the kinematics of this system. Okay. So the first question is, let's identify the number of prismatic and revolute actuators. Okay. So first of all, is this a PPP system, PPRRR system, RRR PPP system, right? So there are different options available to you. And whatever you answer, please keep these to yourself. Again, these questions will be shared to you, and we'll discuss the answers of this question in the next class. And so the first question is, identify the prismatic and revolute actuators in this. And second question is, based on the workspace geometry, what kind of robot is this? Is this a Cartesian, cylindrical, spherical, or articulating robot? Right? Seems like a complex robot which has multiple joints. The first question is about the actuators that are present. Second question is simply about the workspace. So if I just define the workspace of it, how would this robot look like? So please keep the answer to yourself. Please do not disclose the answers here. I would like you to think about this. Look at the video multiple times if you're not convinced. And you may come up with different answers, right? So which is absolutely all right. But let's discuss this in the next time. So please take this as a little bit of a challenge and a homework for next time. Okay. So with that, are there any questions at this point of time? Yeah. Yes, Charlie, please go ahead.
I'm sorry that I mentioned I beg to differ. As far as
that's all right.
this Nadal and Federer, since Nadal is using their both hands, so obviously he'll be getting more power. But I have seen very closely the way normal single-handed backhand player, they are using, they are posing their wrist or arms in a different way than Federer is using. Federer is not using the facing. I mean, the top of the arm is not facing towards. You can watch. He's playing. He just I can't explain. His position of the arm is quite difficult. I mean, different from the others.
Right.
Okay, that's and that way he's getting the power. If you face, I mean, if I give you in a video, I'm just opening my video, I'll be able to explain. So this is the arm that normally the backhand. Okay, but Federer is using in this fashion. In this okay, so that's why he is getting more power.
than the normal single-handed
Okay.
backhand player.
Yeah.
Okay. So this is the technology, or this is the thing that Federer has used for the using the single-handed backhand. Okay. So this is I have watched
Right.
very closely.
That's good homework for me.
Thank you very much.
Yeah, I'm
Thank you
absolutely
very much.
certain that normal players would not. Yeah, you're absolutely, and thank you for that input. So, just to be very clear, I'm not a tennis player. I don't watch tennis that much.
I too,
Uh,
but I love tennis a lot.
okay, that's great to know.
I'm
But
very much fond of Federer also. I'm a very admirer of Federer.
yes, I mean now we have to be admirers because they're both retired. So
Okay.
great points. Yeah, I think so. One of the points that you raised is very important, which is that when we talk about backhand, and differing shots, parallel serial structures, perhaps these individuals are different because they have immense amount of experience and practice with them, and they're gifted, right, in some sense. So I'm talking from a purely biomechanic standpoint, where if you look at the uh, two different approaches, you will see that one has an advantage and the other one has, both have their own advantages and disadvantages. And this is simply to show that when you're practicing, you can perhaps keep this in mind. But you're absolutely right. Probably
You can
Federer has
also,
made,
excuse me, you can also see the position of the left hand of Nadal and the
yeah,
position of the right hand of Federer.
yeah. I mean, you're absolutely right. I mean, they're using very, very different approaches, right? And that is precisely the point. But so essentially, what I'm saying is the body can adapt. It is not about Nadal or Federer. Your body is capable of adapting to make it a serial or a parallel structure. So the contrast was between this and where is it? I don't remember where it is, but yeah, when we were talking about biological structures being serial, we spoke about our hand being one of an examples of it, right? But the contrary to that is because you have two arms, you can make a parallel structure out of it, right? The nuances of this discussion are absolutely appreciated, and I think it's a great takeaway that while they're using different approaches, they seem to have overcome the shortcomings of the serial and parallel structures through immense practice. Right? Yeah, point well taken. So since we are running very, very low on time, I'm just going to finish the first section, and I'm probably not going to be able to touch the AI section today, even though I have a bunch of slides for it. But that's okay. We'll move it to the next class. We'll continue with it on the next class, right? So we were talking about serial and parallel structures. Now, you can always combine these structures, right? So you can have serial, you can have a combination of serial and parallel, right? So you can have serial only. You can have parallel structures where a single end effector is affected. You can have a tree type structure where you have a parallel structure with branching serial structures out. And notice the difference between these two, right? Between the tree type and the parallel structure. Here, there are two actuators that are actuating one single end effector join, maybe this one or this one. Here in the tree type structure, you have a very different approach where there are two end effectors. This might look more like two outstretched arms, right? And then you can have a serial parallel approach where several parallel joints are connected through serial linkages, and then again you have this parallel structure and so on, right? And these have different use cases. Particularly if you look at current humanoid robotic forms, you'll see that they have typically a tree-like structure or very similar to series parallel structure. And this is in order to mimic what our joints do, right? So if you look at the human hand again, coming back to the human hand, and we talked about the human hand being a serial structure. But if you simply look at the elbow and the wrist joint, right, we have two bones, right? Radius and ulna. So there are two bones that control our wrist joint. They rotate with each other. Now, with that, is there a similarity between any of these structures that you see? So if you just look at the wrist joint and the elbow joint, is there a particular structure that comes to mind? The wrist and the elbow joint is what is called a serial parallel combination, right? Because there are two serial joints connecting, right? This is a parallel joint, right? But connecting two serial systems. So this is an example of a serial parallel system, whereas the rest of the joints are all serial. So in effect, the hand is actually a combination of series parallel, and serial joints, right? Effectively making it what are called hybrid systems, right? So hybrid robotic systems. So most modern robotic systems tend to break out of these molds of serial or parallel systems, and then now joining together multiple types of configurations in order to mimic biological function. And what you see are these hybrid structures coming out of it, right? So that essentially brings us to the last application, and we see one application of robotics and two questions. So many of you may have been to modern hospitals and you've seen, big hoardings of this device, right? So this is a modern surgical robotic device. Okay. So what you see is that this device has multiple arms, and you can define what kind of an arm it is. So if I simply look at this portion, right? This portion, let me drop my laser pointer. So if I simply look at this base and this end effector, right? What kind of robot would you say this is based on the workspace geometry? Leaving aside this section. And if I just look at this section of this robot, what sort of a robot is this based on workspace geometry? Is it a Cartesian, cylindrical, spherical? What does it seem to you? Yeah, I think there are some responses. Yes, absolutely right. This is cylindrical. Thank you. Very good. This is cylindrical with an articulating arm, right? So this is articulation, right? And it has a rotational component. Now, additionally, there's a rotational degree of freedom here. And then there are several manipulators, right? Several arms, right? So let's watch a video of what can be achieved with this robotic manipulation. So typically this system consists of an operating station, right? And remember at the beginning of our session today, I had said that please look very closely at how these robotic manipulators are being controlled, right? So if you see that the physician here, the surgeon, is actually has his hands on a robotic platform, which is allowing it to move these robotic arms, right? Right, so he's looking at it in 3D. There's a 3D vision system, and he's able to see what is the system. And here is the manipulating system, right? So it has these sensors at the fingertips, which allow it to manipulate things inside the body, right, through these arms, right? As you will see, these arms all have revolute joints, right? All serial actuators. And inside, you will see this is what is going on inside. So there are different surgical tools that can be used, but yeah, so different surgical tools that can be used, but you can see the level of precision that it offers, right? So in this video, the surgeon is actually suturing a grape, right, inside this chamber. So these are essentially laparoscopic tools that are being inserted and being manipulated. The end effector, right, which is this grasper, is being manipulated by the surgeon. So the movement of the arms of the surgeon is being translated to this end effector effectively, while also correcting for some of the variations, right? So when we naturally move our arms, there's a little bit of shaking. We know surgeons are very steady hand. Even then, they have certain amount of variation. So all of those variations are being sort of canceled out by this robot, right? While providing the ability to move in such confined spaces where a surgeon would not be able to otherwise operate, right? And you can see there's a scalpel and a scissor which is being used to cut the sutures. Right? So this is what happens inside this robotic system. Right? So this is the Da Vinci system. So by and large, if I look at this device, this consists of an operating station, the surgeon's control station, where there are instrument manipulators which are used to move the end effectors. And then you have these robotic arms which have multiple tools, and this can be adapted based on the kind of surgery, where this can be used for laparoscopic surgery, it can be used for orthopedic surgery, and so on and so forth, for positioning, and so on and so forth. Right? And then there's a system that controls all of this. So there's a control system, there's a sensing unit, and then there's an actuation unit. And these actuation units consist of multiple robotic arms. So now the question is, if I look at the definition of industrial robots, as we had stated, reprogrammable, reconfigurable, automation systems, right? Automated. Does this qualify that definition of a robot or an industrial robot per se? So the question is the Da Vinci robot an industrial robot as defined by the ISO 8873-2012 standard? And there are already some responses. Okay, good. I like a debate. So Amit says no. Agnishekhar says yes. And Joydeep, I think he had mentioned in the very beginning that he looks at this as a cobot. Yes. Okay. And I fully agree with you that the answer as per the industrial robot definition is probably a no. And it is probably not a robot as per that definition, but it is definitely a robotic system, right? There are multiple robotic parts in it. It is being controlled in real time using through a human operator, but there are multiple stages of processing that are happening that allows it to collaborate, like Joydeep and others have said, in order to be able to operate this device successfully, right? So there's a fair amount of decision making, a fair amount of intervention that the robot is doing on top of what the surgeon is doing. Right? There's a fair bit of intelligence that is helping the surgeon achieve the level of control that he or she is achieving. Hence, there is a closed loop system inside this Da Vinci robot that is taking small corrective actions, small preventive actions on top of what the surgeon is doing. So it is a semi-autonomous system in its own regard, right? Semi-autonomous, absolutely not autonomous, but semi-autonomous in its ability. And therefore, as per the standard definition, it would not fit. But that brings us to the question, how do we again define robots, right? In the modern era, does the old definition of an industrial robot still hold? Do we need to expand it? And the answer is absolutely yes. We're going to look at this evolving definition of robots as we move through the course. And we'll challenge these definitions as we move through the course. So with that, I know it's pretty late. It's 2:43. So I'm going to end the session here today. We're going to talk about the role of AI in the next lecture. I have a bunch of slides, and I'm going to continue on this theme so there won't be any discontinuity whatsoever. Okay. Thank you so much. If there are any questions, I'll be happy to take them. So I think somebody asked, although this is an accurate system, but isn't it slower than human? So the Da Vinci robot, if you look at the specifications of it, right? Technically, it's faster, but in a surgical setting, the speed is not of paramount importance, right? In this particular case, the importance is placed on the precision. And in fact, the reason why people prefer robotic surgery over a traditional surgery, although if you look at the evidence seems to suggest that there's really no difference between a robotic. So, for example, my mother had a bilateral knee surgery, right? The doctor recommended that we do a robotic surgery. But if you look at the literature, it seems to suggest that the end outcomes, right? Recovery, mortality, the ability to walk, all of these parameters, a normal surgery is no worse than a robotic surgery. However, a robotic surgery allows you to do one thing, which is very important, which is that it is somewhat minimally invasive, right? So essentially in a robotic surgery, you're going to be able to make small ports, which allow you to make very, very precise movements. Now, those precise movements mean that you'll have to make less incisions, less cutting, and perhaps less, less time to recovery, right? Although these have not been validated. So in most cases, in surgical and medical robotics and medical cobotics, the key is precision, most likely not speed. So in this case, these are highly accurate, highly repeatable systems. We'll look at how these systems are actually calibrated in a future lecture when we talk about sensing and actuation. Right? So yeah, but very interesting devices, very versatile devices. And although the medical industry wants you to believe that these are the best things that have happened, the evidence seems to show otherwise. Right? The evidence seems to show that surgeons are just as good with or without these tools, right? So that makes you wonder whether these are really cobotic systems or simply another tool in the arsenal of a trained surgeon. Right? It ultimately boils down to the skill of the surgeon. All right. Yeah. So somebody has mentioned similarly fatigue on that position when human do is very high. When it's a robot, he's sitting and he's comfortable. That is also a very good point. So typically in orthopedic surgeries, which is where most of these Da Vinci robots are being used, and in minimally invasive surgeries, the load and the fatigue on the surgeon is extremely high, right? But with a robotic system, most of that load, most of that cutting force is being generated by the robot, and therefore a lot of that load is prevented, preventing fatigue and probably surgical errors. Very good point. That's nowadays there are pneumatic-based, silicon-based grippers also used for uneven surfaces. Yes, absolutely. There are. We are going to we have a separate module on soft robotic actuators, not module, rather a separate lecture on soft robotic actuators, where we will be talking about specifically about this. So there's a website called Soft Robotics Toolkit. So if you're interested, you can build one yourself, which gives you all the tools for building your own soft robotic grippers. It's a little difficult, but it is possible. Yeah, thank you, Joydeep. Joydeep says lots of new interesting topics, very new to me. These are purely part of mechanical engineering. Thank you very much. I appreciate your time, and thank you so much, everyone, for spending so much time on a weekend. This is the first lecture. We're just getting started. All the references, all the websites will be shared with you. Please don't worry. All the slides will be shared with you. All these materials are yours to take home. So please go over whatever you can, and please stay updated, right? And I'll see you again in the next class. Thank you. Thank you so much, and I'll see you next week. Bye-bye.
Bye, sir.
Bye. Thank you.
Thank
Thanks
you
a
all.
lot. Bye.
Thank you, Professor. Thank you.
Yes. Thank you. Thank you. Thanks. No, Vinita, we don't have a class tomorrow. So remember that our project sessions actually start later this month when we have the project kickoff. So there's going to be only classes on Saturdays from now on, and we'll let you know in due course of time when the project sessions, which are scheduled on Sundays, will start. Okay, so no class tomorrow. Yeah. Thank you very much. Please refer to the schedule that has been shared on LMS. Thank you very much. Thanks.
And sir, by what time the recordings will be available? Actually, I was not able to attend last session.
Okay.
So I'm not.
So this is a Times Pro question, but I believe the session recordings become available the very next day. Usually these are 4 or 5 hour lectures, right? So sometimes it takes a little bit of time, but Times Pro is quite prompt in uploading the lectures. They'll be available on LMS through the Zoom Teams recording. If there's somebody from Times, would you be able to clarify that?
Yes, sir, Aman, they said. So, sir, by EOD, it will be uploaded.
Okay, so by end of day.
Yeah.
Okay.
Today, by end of
Great.
the day, it will be uploaded.
Yeah.
Regarding the slide, it might take a couple of days for us, right? So we are all doing multiple other things, but slides, everything will be shared with you on the LMS. Okay.
Okay, Aman, one more thing you can tell. There was in the Times Pro, your portal, it's mentioned that session will be recurring at 9:30. What does it mean? I was not able to make.
Not tracking. You can just check your time zone. It should be India GMT 5:30. As I mentioned in the
Okay,
technical
fine.
orientation,
Right.
just check it. Okay.
Got it. Thank you.
Yeah.
Okay. Thank you so much,
Sir,
guys. Take care. Bye-bye.
one question, I'm so sorry. It's regarding the project. Actually, the kit, I don't live in India, I'm living in Central Europe. So about the kit, I don't have anyone from my family living in India. So how would be the kit shipped to me?
So we will talk about so we have had participants from abroad
Okay.
previously. So we have provided them options of buying kits online
Okay.
from other sources as well. So we'll try and help you with that. We've
Okay.
had people from Europe, we've had people from USA, Singapore, from the Middle East, so from all around the world, and they've all received kits.
Okay, sir. Thank
So
you
we'll
so
make
much.
that happen. Yeah, thanks.
Thank
Take care.
you.
Bye-bye. Bye.
Bye-bye.